Well, hi, everyone, and welcome to AI Infra at Scale 2024. My name's Damien. I'm an engineering director here at Meta, supporting the PyTorch team within AI infrastructure. And it's really exciting to be kicking off this event. At Scale is this amazing opportunity for, I think, all of us as an industry to come together and talk about some of the biggest challenges that we see in scaling, all of our infrastructure to ridiculous heights, anywhere from how do we serve billions of people efficiently and reliably, to how do we store insane amounts of data, to how do we build the hardware and the data centers that power all of this, all the way to how do we help the products that we're building on top of this infrastructure really benefit from that, which is going to be a topic of the next at Scale, which is just in a couple of weeks. Now, we're here to talk about AI, and last year, around this time, was the first time we've held an AI Infra at Scale. And this was the first time we all really came together to talk about how we build unique infrastructure to solve the really big challenges that we have to power the AI revolution. And I think it's fair to say in the last year, things have only gotten bigger, more complicated, more interesting, and honestly, more fun for all of us. So it's really awesome to be here opening the second AI Infra at Scale. But also at Scale is really about more than just sitting here and listening to a bunch of great talks. It's about building a community with all of us. So this is also the first time we've done this in person. And I really hope you'll take advantage of this to meet some people, talk about kind of the things that you're seeing and that are most interesting in your world, and kind of share some perspectives on that. So with that, we have a great program lined up for you today. We're going to start off with a keynote. I'll tell you more about that in a second. And after that, we thought it'd be cool to really talk about the journey, kind of the AI journey all the way through a stack. So we're going to start off with really how do we build delightful experiences for our customers. And in AI, that comes from building the biggest and most effective models that we possibly can. So the first part of our content is going to be around Llama and how we actually built the latest Llama model. I'm hoping most people in this room know that we just released, just last week, Llama 3 405B. And you're going to hear all about kind of everything that went into building that, all the way from data to training, and to inference and how we serve it. So after that, we're going to pop down one level down in the stack, and we're going to talk about the frameworks that power all of this. And there, I support a PyTorch team, so I'm kind of biased. Obviously, we're going to talk about PyTorch, and I think that's pretty cool. But really, it's all about open innovation and how we leverage open source to kind of band together and bring kind of the entire community forward, and not just kind of invest in one kind of closed solution. So you're going to hear from Databricks first, and how they're thinking about open source innovation, and of course from the PyTorch team. And after that, we'll go to one level down in the stack, and that's talking about hardware. There's a lot of innovation in hardware for AI right now, and there's also a lot of innovation in how we develop hardware and models together. And we're really able to leverage the best capabilities of both by doing this co-design. So that's going to be our main talks. We'll wrap up with a panel of industry experts. We're going to talk more about sort of future-looking things around where they see the industry going, what trends they're looking out for, and kind of what's coming next.
Welcome to the virtual edition of AI Infra at Scale, following our live event at Meta's campus last week. My name is Chris. I'll be your guide through our content today. We have a fantastic afternoon ahead of us. Kicking us off is our keynote speaker, Aparna Ramani from Meta. Over to you, Aparna.
Hello, everyone. Thank you all for coming, and welcome to AI Infra at Scale. What a year it's been, right? AI dominates the headlines across the tech industry, with bigger, better models, new AI-powered applications, and for those of you here, lots and lots and lots of GPUs. But before we dive into where we are today, I'd love for us to zoom out and talk about how we got here so we can put this moment into perspective. And a lot of this history is probably familiar to you all, but please bear with me because we cannot do justice to the history of AI without going all the way back to the 1950s, when Alan Turing famously asked the question of whether a machine could think. And there was an initial period of enthusiasm at that time that was followed by a long AI winter. But things pick up again in the late 90s, and many people attribute the thawing of the AI winter to Deep Blue. For those of you who remember this, Deep Blue in 1997 from IBM beat world champion Garry Kasparov in a chess match. And Deep Blue was powered by almost 500 custom chips, and it could process about 200 million chess moves on a per-second basis. And for a minute there, people thought that Deep Blue was the future. But in reality, it would turn out to be a high watermark for this kind of hand-coded computer intelligence. What followed next were neural networks. What's now known as a convolutional neural network, or a CNN, was first introduced by Yann LeCun back in the 1980s, and it's gone through several evolutions. In 1998, LeNet-5, a CNN, was able to correctly recognize handwritten zip codes from over 60,000 post office samples with over 99% accuracy. But CNNs were notoriously hard to train. And so people for a while favored recurrent neural nets because you could train them sequentially. But this would change in 2012 because AlexNet comes along in what's sometimes called AI's Big Bang moment. And AlexNet was a much bigger CNN than LeNet-5. It was trained on one of the largest image datasets at the time, ImageNet, with over 14 million images, and it was trained on all of 2 GPUs. AlexNet resulted in this step change improvement in labeling images, and it created all kinds of breakthroughs with image recognition. But what was perhaps a more important breakthrough was that AlexNet demonstrated that it was possible to parallelize training in a CNN. 5 years later, Google releases the paper, Attention is All You Need, introducing the concept of a transformer model. And this leads to all kinds of large language model innovation, BERT by Google, followed by the Generative Pre-trained Transformer, or GPT. In 2021, diffusion models break on the scene with DALL-E introducing amazing text-to-image generation. In November 22, all of these model breakthroughs reach public consciousness when OpenAI launches its chat interface, ChatGPT. In 23, we at Meta make Llama 2 openly available for research and commercial use. We follow that up with Llama 3, both a 70 billion model and an 8 billion model in April. And just last week, we launched a 405 billion parameter model, Llama 3.1, the first frontier-level open-source AI model. And this triggers an avalanche of innovation across the industry, with an entire ecosystem being built up around Llama. And so it's interesting to look at that whole decade between AlexNet and GPT and contrast that to the speed and the intensity of innovation that's happening now. So many of you across the industry have worked together to contribute to a deeper understanding of AI that we have now. But since this is an AI Infra at Scale event, I want to talk about how all of this model innovation connects to infrastructure. There's always been a symbiotic relationship between the evolution of AI research and the evolution of infrastructure. The availability of compute, distributed systems, large-scale data processing have all contributed to all of the innovation we see in AI today. And similarly, the AI roadmap has helped shape the infrastructure roadmap. So now, not going to walk you through the whole history of data center computing, but really simplistically, for decades, data centers were dominated by a CPU x86-based architecture. But it turns out GPUs are way better at floating point arithmetic, which is at the center of how models learn. And so here you can see, as of 2012, the volume of data center GPUs is pretty negligible. You start hearing about large research clusters. In 2017, we at Meta create our first research supercomputer. And you start seeing data center GPUs kind of get a little bit more. This is the graph after ChatGPT is released in 2022. And by 2023, it is clear there is an explosion of GPUs. The shift is fundamental, which is why you'll hear today's computer is not a PC. Today's computer is a data center. And now you're hearing GPU clusters in the tens and thousands for just a single training job to be run, and fleets in the hundreds of thousands. In our own fleet here at Meta, we'll have 600,000 GPU units by the end of the year. And by the way, this is in addition to all of the CPU infrastructure that we already have, so we can run multiple parallel workloads. So that brings us to today. Our ambition as an industry and a society have grown since those early days of Deep Blue and AlexNet. Today, we talk about generalized intelligence, where machines can perform tasks, even complex ones, on par to humans, maybe better than humans. And irrespective of where you are on the spectrum of extreme skepticism to hopeful optimism, there is no question that there is still a lot to learn, and we're still early on this journey. So let's talk about some of the challenges we face as we continue to scale these models towards those big, lofty goals. Today's models have been improving predictably based on 3 inputs. One is data, the second is compute, and the third is algorithms. So number 1, data. The data required to train these models is enormous. With each model training generation, we keep adding more data. We're talking trillions of tokens. Just for an example, Llama 3.1 was trained on over 15 trillion tokens. And on the infrastructure side, we've made a lot of advances in how we load and prepare data for training, but also in how we extract signal from data, quality signal. And we're continuing to evolve our data pipelines and our data warehouses to be able to scale with AI. But there is a bigger, deeper challenge here. There is a growing recognition that data might end up being the bottleneck, even in the short term, in the next few years. And there's various predictions about it, about when we'll reach full usage of high-quality human-generated data completely. Let's think about that for a second. There is a point in time, somewhere in the near future, when we would have exhausted all available human-generated data for AI training. And that's unfathomable. So what are we going to do about it as a community and as an industry? Well, we have to work on getting major efficiencies in the data itself and data processing and just like the quality of data. But there are also efforts across the industry in being able to produce synthetic data, where we have models producing their own data and then models evaluating themselves and so on and so forth. And this is really, really exciting work. This brings us to the second primary input, and that is compute. And this one is close to all of our hearts here at scale. Conservative estimates put the growth of training at about 4 times a year for large models across the industry. And assuming that scaling continues here, there are a bunch of infrastructure challenges that we're still working to solve. The first is obviously just buying or producing massive amounts of GPUs. These chips are pretty expensive, by the way, and there's very few people manufacturing them. And about a year ago, I don't know if you all remember, there was a pretty big supply chain crisis that was hitting us all across the industry, and everyone was hunting for GPUs. And we used to joke, trying to buy a GPU during the supply chain crisis is like trying to buy toilet paper at the height of the pandemic. So what are we doing to mitigate this risk? We at Meta, like several other companies, are building our own custom silicon. A huge advantage to building our own silicon is that we can optimize the silicon for our own workloads. And that way we get a huge advantage both in cost and in performance. Beyond that, a huge bottleneck to having these large clusters is just the sheer energy consumption. It's no secret that GPUs are incredibly power inefficient. Each GPU uses somewhere between half a kilowatt or a kilowatt of power. But guess what? The human brain, all of the human brain, uses about 25 watts. So we're off by a huge factor here, and unless we build on some real innovation here with energy, energy will become a real bottleneck in our ability to scale. And then you have scaling challenges during training. As you know, GPUs must be interconnected and computing in parallel during training. And unfortunately, if a single GPU fails, the entire training job stops because the model is no longer in consistent state. And so today, every time there's a failure, we fix the problem, restart training, and there you go again and again. And stopping and restarting is pretty painful, but it's made worse by the fact that as the number of GPUs increases, so too does the likelihood of a failure. And at some point, the volume of failures could become so overwhelming that we lose too much time mitigating these failures, and you barely finish a training run. So what are we doing about this? This is a huge area of focus and investment across the industry, and we're working on everything from trying to reduce the time that it takes to detect a failure, to quicker restarts, to all the way to new research paradigms around asynchronous training and other research ideas that no one's tried before. And so this is going to be an exciting area to keep an eye on. But beyond what I just mentioned, there are a ton more challenges we're working towards. Networking needs completely to be revamped because we're dealing with large-scale networking with GPUs interconnected and communicating with each other, that the protocols don't scale anymore. There's the fact that all these interconnected GPUs are so hot that existing data center cooling techniques don't work. So we're inventing new kinds of cooling technologies for data centers and keeping GPUs cooler. So the list of awesome engineering challenges we have goes on and on. We talked a bit about data and compute. Let's talk a little bit about the model algorithms themselves. And research here is evolving pretty quickly. And on the infra side, our job is to make sure that we bring these research breakthroughs into production and into the community as quickly as we can. And the algorithms themselves, there are maybe a few schools of thought that we should touch upon about what will lead to generalized intelligence. First is the scale is everything camp. You can see that in language models particularly, when well-trained, a model size is still the biggest predictor of performance. It's a hot point of debate right now, though, on whether these models, which are getting better and better at sort of next token prediction, will be able to make leaps towards better understanding reasoning, being able to look at ideas and draw conclusions, whether they'll be able to apply reason and causality and all the things that are common to human intelligence. So a second school of thought says that models need a more grounded understanding of the world, an understanding that comes from explorations, experiments, interactions, similar to how a child interacts with the world. Thus, there is an hypothesis that we need world models that can be used to run forward simulations with increased planning and increased accuracy. And this belief has driven some of our own research work in our research labs here, where teams are working on something called Joint Embedding Predictive Architectures, or JEPA. And so much of how machines learn is so much less efficient than how humans learn. Machines can grok new information, but it takes billions of parameters and exposure to tons of similar information, whereas humans can learn something, immediately derive some insights, and then use that to make decisions. So there is a third hypothesis that argues that we should look at the human brain for clues on new model architectures. And within all of this debate, there's the question of when you're probably asking too, which is how soon? How soon will we get to generalized intelligence? And so I'm going to make a prediction about this. No, I'm just kidding. I'm not going to take a position about whether this is going to take 2 years or 20 years. But here's what I do know and believe. At the moment, given the sheer size and scale necessary to support this kind of innovation of foundation models, there are very few entities in the world that are able to do this. And so we're seeing two different approaches emerge, a closed approach and an open approach. And we've been pretty public here at Meta about the fact that we're taking an open approach here. Generally speaking, an open approach distributes innovation and serves as a countervailing force to a concentration of power within a few entities or even one entity. And I think that's pretty cool. And in terms of the models themselves, we've set out to build models that are competitive with the best proprietary models. I directionally expect that we will continue to be able to open source these models as long as we are able to. But we also have a long history of open sourcing our underlying infrastructure. Whether it's the Open Compute project, where we open sourced our data center designs, or React, which is used for building user interfaces, or closer to home, PyTorch, the most dominant machine learning developer library out there. And so we will keep building on all of this as a community. This is such a great time for us as technologists. The next several years are going to change the way that we work, the way we go about our lives. And as we saw earlier, there is no one company or research group that has been responsible for all of the innovation we've seen so far. Progress is moving fast right now, in part because we are all coming together and building on top of each other's discoveries. A paper gets published, libraries get released, a new open source model gets announced, and that is the spirit of at scale. I really hope that you'll all learn something today and also share your thoughts and ideas, but even more than that, I hope that you'll leave feeling inspired to tackle some of these challenges ahead of us so we can all push on the next frontier of AI together as one community. Thank you all for coming. Hope you have a great day.
What a great way to start the event. Thank you, Aparna. Next up, we will hear from the Llama team, starting with Joe Spisak, about bringing Llama 3 to life.
Hi, welcome to Llama Open Intelligence, everyone. I'm Joe Spisak, Product Director at Meta, focused on our open source and ecosystem. So it's really exciting that LLMs, especially Llama, are really becoming foundational to this next wave of AI. And it's not only the LLM, but also things like text-to-image generation, or even AI-enabled creator tools that basically take the power of all of this AI and put it into the hands of those who can build new things and new applications. So there's three things I really want to talk to you today about. One is really our open approach with Llama, the systems that are actually forming around Llama, so it's not just a model anymore, but really a system and really ultimately an agentic application. And then three, how we think about trust and safety, and especially the tools and the ecosystem around us in open trust and safety. So just kind of taking a step back and looking at where we were and where we've come from, it's actually a pretty incredible journey from Llama 1 back in February to Llama 2 in July last year, to the Code Llama and code generation models we released last year, as well as Purple Llama for open trust and safety, to most recently April with Llama 3, and last week, of course, the big bang we had with Llama 3.1 and the 405B launching. And all along the way, we've been releasing system-level components that help you to build Llama much more responsibly and much more safely. So just zeroing in on the 405B for a second, we are really excited about this model, and we're really excited that we were able to open source it. We really feel like this is going to supercharge innovation, open up completely new application areas like synthetic data generation to improve smaller models. And this is a model that is open weights, open source. You can fine tune it, you can distill from it and create smaller models. You can deploy it yourself on your prem. You can even distill it onto a mobile device. So really it gives you the full freedom to take this frontier class model and really make it your own. And when we thought about the 405B and this new class of models we built, we started with simplicity. And the architecture is an autoregressive transformer architecture. It uses special attention to make it faster at inference time. But ultimately, we pushed on scale. We pushed on the scale of data, and we pushed on the scale of infrastructure when we were training it. So when we thought about data, it was how much further can we push data? And we ended up around 15 trillion tokens, which is some of the largest data ever trained in LLM, and then 16K H100 GPUs. This is by far the largest infra we've used to train a Llama model to date. And the results are spectacular. If you compare Llama 405B, and we've done this across over 150 benchmarks against some of the top models in the world, Llama 3.14/B definitely stands and compares really well to GPT-4o and Claude Sonnet 3.5, which are considered some of the best models in the world today. And it's not enough to do, kind of standard evals and static benchmarks. We also look at how humans and how people actually interact with our models and how well they perform. And you can see here, Llama 405B compared to, say, the GPT-4o or Claude Sonnet stands as well really well. I mean, does a really good job. The people loved interacting with them. This was over almost 2K prompts and over use cases like, say, being a coding assistant or a multilingual chatbot. And so we take a step back and think about, why open source is good. It's really good for developers. As I mentioned, these weights are weights that you can download, you can modify them, you can create custom applications on them. You have the full freedom to do what you need to do for what you need. For Meta, it gives us a chance to accelerate our development. There's new things happening in the community every day, and being open and building that bridge helps us to move faster and learn faster. And then really the world and how we democratize this technology and provide it for everyone, it kind of levels the playing field for the entire world. And our ecosystem is also flourishing. The ecosystem around us is not only enterprise, but it's also platform developers, startups, those building differentiated offerings like, say, Grok for really low latency inference, all the way through to our hardware vendors who are accelerating Llama models on various platforms. This gives the whole community kind of this platform to build on and really accelerates kind of all aspects. And you can see some of the launch partners we had with the 405B. Every checkbox here was a labor of love and night or a weekend or a lot of effort from a lot of engineers to make this happen. And you can see all the various use cases and workflows that are enabled on day one with the 405B. From, say, Databricks to Dell to Grok, you can see all the way from inference to model distillation to synthetic data generation services. We really have a full gamut of services available for developers on day one. So let's switch gears and talk about the Llama system, because the model is only part of the story. And we think about how models actually fit within these agentic applications. We're evolving very quickly to having system safeguards and customizable system safeguards that you can then fine tune and customize for yourself. And today we call those Llama Guard or Prompt Guard. We'll talk about more in a second. But there's also tool use and how you actually plug in these models with, say, outside tools or plugins, or think about it in terms of like a search application, or say calling a calculator, because sometimes LLMs don't do math very well. So really building this whole capability, but with the model itself at the center of it. And we actually open sourced all of this. So we have a full repo. It's called Agentic Systems in the Llama repo on GitHub. And you can actually play with all the code yourself. And so we've also taken it all the way to demo apps. So you can actually build on our own demo apps that we have that use all of these components. In this case, what I'm showing is code generation and say like a coding assistant, where the LLM will generate code. It'll actually execute the code through a code interpreter. You can see it's generating some nice graphs using something like matplotlib. And ultimately, you can use this as a way to kind of build on top of it and kind of customize for your own. So it's not just the kind of the raw code. We actually provide end applications. And the last thing around systems is we're also working with the ecosystem to build and support kind of standardized ways to integrate with Llama models. And we think this is really going to accelerate kind of the world around Llama and the ecosystem. And we have an open RFC. It's linked here. It's on GitHub. We had dozens of comments so far. And ultimately, we want this to be kind of the glue that brings this community together and helps accelerate the overall ecosystem. So let's switch over to trust and safety, something near and dear to my heart. So when we think about trust and safety, and we think about the development process we've taken to develop these models, it really starts with the data and how we think about things like representativeness of the data set itself, how we think about evaluating that data for things like harmful content, filtering, benchmarks and evaluations. We obviously do some model level work as well. So we do things like safety fine tuning, but ultimately we bring humans in the mix at the end, or actually iteratively, things like red teaming. And when we try and jailbreak our models or understand what situations these models are going to be in and actually have real humans interacting them, so we can actually iterate quickly and understand how to improve them, version over version. And so when we think about open trust and safety, one of the things that we thought about early on was we really don't want to compete on safety. It's not something that makes sense to compete on. We really want to do this as a collaborative effort, and hence a lot of our work in, say, AI Alliance and what's called really Purple Llama, which you can see some of the components here. And much like the system level components I talked about earlier, some of the things we've released are Llama Guard, which is a open model for prompt filtering, input and output, Prompt Guard for prompt injection attacks, Code Shield for things like insecure code generation. And ultimately, we have, I would say, the state of the art in cybersecurity evaluation, and we just released version 3 of that. And so kind of putting some numbers behind all of this, we've been at this in terms of research for over 10 years. The fundamental AI research team is world-class in this research. We publish system cards for our products, over 20 of them to date. We have over 100 members in AI Alliance, where we founded that effort with IBM last year. And we've open sourced over 1,000 projects, including PyTorch, obviously heavily invested in Llama, React, and a whole bunch of other projects. So this was incredible. Obviously, the models are fantastic, and we're really excited about what the community is doing with them. But the challenges to get here and what we had to overcome were definitely unique. And I'm really excited to hand it off to Delia to talk about the data infrastructure scaling work we've done, KV to talk about training and how we scaled up to that crazy 16K GPU number, and Charlotte for how we deployed at Inference efficiently and actually built real applications out of all of this.
Thank you, Joe. I'm Delia, and I will next share some of the cool insights about Llama free data, as well as our investments towards data products to accelerate researchers' impact. As we build new versions of Llama, we invest in more tokens of higher quality and of better diversity. Notably, Llama 3 is trained on 7 times more tokens compared to Llama 2. It is multilingual, and adding languages beyond English required us to optimize the tokenizer for the best performance at inference time for non-English languages. This meant we had to increase from 100K vocabulary size to 128K. Data quality has been a major investment towards the model performance. And in the case of web documents, we have added 2 new quality methods. The first one, which we call Wikipedia Score, measures the probability of any single document being referenced by Wikipedia. And second, we have used the previous versions of Llama to assess the quality of every single document that was candidate for training. Llama 3 brings significant lift in code, math, and in general problem solving and reasoning. And this has been enabled by better sourcing, extracting, and processing of such data, as well as very cool investments in synthetic data. I will give a few examples of the synthetic data investments. In the case of code, we add comments automatically, we add unit tests automatically. And we are using a process called rejection sampling, where the model generates tens of examples, and we use code execution signal as a feedback loop to decide what to keep and what to discard. We are also using synthetic data to annotate very long documents or long context, where it would be infeasible for humans to read such long documents at large scale. Data diversity comes in many forms: diversity of languages, diversity of modalities, and diversity of topics. In the case of languages, Llama is open source. Facebook, WhatsApp, Instagram are deployed across the world. Over time, we want to make Llama understand all the languages of the world so that it can speak to everyone and bring state-of-the-art AI to everyone in the world. Text comes in many forms. Web documents can be short, 2 pages long, or we have seen cases of extremely long web documents of tens of millions of characters. Then there is fast-changing short messages in form of dialogue, and we have code in all sorts of programming languages and all sorts of formats, from a simple function to an interview question, to a coding contest problem with unit tests, to an entire repository. And there is a lot of synthetic data advancements we have done in the case of code, and a lot of tricks in terms of how you flatten a repository into your context window. And then there is documents with heavy formulas like math and physics documents. And we have also noticed that interleaving code and math with text in the so-called editorials has helped the model. Llama 3 is trained on a wide diversity of topics, from historical facts about the world to sports, business, science, anything, you name it. This enables the model to build a very detailed description representation of the world, and it enables it to answer questions across a broad diversity of topics and across different degrees of difficulty. We use all this data for training multiple stages of Llama, from pre-training to alignment to several stages of fine-tuning. And we also use it at inference time when users interact with MTIA across our various product services. In particular, we index documents that are post-training time into our search engine, and we retrieve the relevant ones when the users interact with our products. Next, I will talk a little bit about the data lifecycle. For each type of modality, we need to decide where to source the data from, but it's equally important to also decide where to not source data from. In the case of web documents, for example, we don't want to get content that has too much concentration of personal identifiable information or adult content. With this data collected, we run several mitigations to make sure our privacy and integrity bars are met. For example, we want to remove documents that have harmful speech. And then to deeply understand every single document, we run a series of signals, such as language identification or various topic classification models. And we have a very extensive data curation pipeline, which I'll talk about in a bit. The purpose of the data curation is to filter out lower quality content. We have run extensive number of ablations or experiments before training in order to decide the best data mix we use for training. The data mix means the composition of different types of data, sports, art, math, code, as well as the degree of repetition. How many epochs should you run across your math content? We run this data mix on a model of smaller scale but the same structure as Llama, and we evaluate it on the same set of benchmarks, reasoning, language understanding, multilingual, that we evaluate Llama on. And this enables us over time to correct gaps in our data and to come up with the best data mix for pre-training. We noticed, for example, that the internet has a lot of arts and entertainment, and we don't need that large amount to train Llama, so we downsample this content. We also noticed that upsampling science in general, math code, has helped the model performance. And we have done this throughout training and in post-training, including in a process called annealing, where we added more code, more math, and you can read more about it in our recently released paper. We create feedback loops from both data curation and from data ablations back into data collection. And these feedback loops enable us to decide what to collect next, focusing on higher quality and focusing on closing diversity and data gaps. Data curation for web documents starts with filtering out bad documents. We do this even at the URL level, and then extracting the content. We run a set of heuristics or statistics on top of these documents. You might have heard of the DeepMind's Gopher heuristics. You might have read the paper. So those are some of the kind of heuristics we are running. And then we run a set of deduplication algorithms to eliminate documents that are exactly the same, documents that are approximately the same. We use min hash algorithms for this. And also, we want to deduplicate lines that are very common, especially across the internet. And we are not in a one-size-fits-all situation. You want to eliminate lines heavily repeated in web documents. Those could be boilerplate. But you don't want to repeat lines that are heavily occurring in Python, for example. And then we run a set of language heuristics, language identification, and a set of models to assess the quality of the documents and the various topics in each document. We run all this pipeline in PySpark, and we use a lot of open source ML libraries that this community has helped build. Some examples are Presidio, various tokenizers, Beautiful Soup. Whenever we have to redo our HTML extraction or improve our quality algorithms or improve our deduplication models, we have to redo this entire pipeline across a very large corpus of data of hundreds of billions of documents. This is very expensive. And we have also observed data skew, where some documents are short, some are very large. So we had to dynamically shard the data into multiple buckets and parallelize execution in order to improve the efficiency and the latency of this pipeline. And with these changes, we are able to process tens of billions of documents within a day and create those feedback loops very frequently back into data collection. Our researchers are spending many hours to understand the data, compare data sets, compare training samples. And we invested in data products and tools to enable them to understand data faster, to make decisions faster, and to innovate faster. These tools include easy navigations of short and long documents of any kind, math, code, web documents. And they include tools to compare data. And they include more advanced capabilities, such as integrating with Llama, where you can ask Llama anything about a document. And this has been particularly useful for very long documents where you don't have time to read through the document. We also added click of a button translation, which helps with multilingual, and we added collaborative capabilities such as annotating documents, adding comments, sharing documents with your colleagues, which have been very valuable for fine-tuning and eval data sets where data quality is even more important than it is in pre-training. We also generate data insights out of the box for all our training data sets. We create distributions of the data across all the signals and all the heuristics we compute. We also detect outliers. And one cool example is detecting repetitive text in Llama answers, such as the model repeating, "I'm sorry, I'm sorry, I'm sorry." With these tools, our researchers were able to quickly detect such problems and correct them. So this gives the researchers a flexible platform for them to just move faster with data and improve the data quality. We have a lot more work in progress around multimodality, synthetic data, agentic behaviors, which we'll talk about over the next few months. Thank you. And I'll pass it to Kaushik to tell us some of the cool insights about training.
Thanks, Delia, for that fantastic talk on data. My name is Kaushik Veeraraghavan. In the next few minutes, I'm going to talk to you about how infrastructure has enabled the training of our large-scale LLM models, culminating in Llama 3.1 that you've heard about earlier from Joe. But before we jump into Llama, let me start off with a little bit of history. Meta has been a deep proponent of AI, and we've been using it really intentionally for the past decade. Specifically, if any of you have ever opened up Facebook or Instagram and looked at your newsfeed, or have ever clicked an ad, well, that's our AI models for ranking and recommendations at play. So we've been deeply invested in this space. What's changed in the past year, though, is the scale at which LLM training has shown up and how we've evolved. Specifically, while we've been using a bunch of AI training for ranking and recommendations, most of our jobs ran on small numbers of GPUs, maybe up to 128 of them. LLM training is completely different, and we need to rapidly scale to hit 1K, 2K, 4K, and eventually 16K GPUs for a single training job, as you've heard from my friend Joe Spisak. In the next several minutes, I'm going to talk to you about what this means and how we've scaled. But to just plant an idea in you, the scale at which you're operating at is similar to planting a seed and then growing an entire mature tree in a single year. This is just crazy growth. In order to enable this, there's really two parts of the problem. The first is the physical infrastructure. We need to make sure that we've invested deeply in building out a foundation, which starts with the physical infrastructure, the data centers, the networks, the hardware, and so on that power our AI ambitions. And next, we have to invest deeply in building out the software stack and build out the operations muscle in order to be able to run these large-scale AI jobs. In the rest of my talk, I'm going to go delve deeper into a few things that we've done at the physical infrastructure layer and several decisions we've been making at the software layer in order to enable this massive growth. Also, as Joe mentioned, we are deeply committed to open source. I'm going to share with you how this open source thesis pervades a bunch of our work across infrastructure, and I'm going to hit on several notes on how we really believe in open infrastructure throughout our stack. And then I'll close out by speaking not just about what we've done and reminiscing in our Llama journey, but also thinking about the future. What do we anticipate running into in the future, and how we look to the broader community? So let's start off by diving more into our open infrastructure. Specifically, as you might have seen again from Joe, or maybe you heard from Aparna or other speakers who are talking about our AI work, Infra is deeply committed to the idea of open source and open infra. Specifically at the physical infra layer, we've been champions of releasing all of our data center designs and our network design via our open compute and open network initiatives. At the software layer, we regularly release papers for things like our scheduling systems, such as MAST, for our storage systems, and many other things to the academic community. And finally, we are super excited to release the code for a bunch of our products, and then even entire models themselves, as you're seeing with the Llama 3.1 release. We also do things like write blog posts, which cover what are our cluster designs, how do we operate them, and then share a bunch of learnings about operating this massive infra to enable all our AI work. Now, let's dive deeper into what are some of the details of our infra. I'm going to start off by speaking about our physical infra. And in the interest of time, I'm going to give you a couple of examples and insights that explain to you why we're building certain things and the problems that we're trying to solve. So at the physical infra layer, the first thing that we realized was that we had a bunch of data center footprints, and we could use this to power our applications and to enable all our AI needs. However, we quickly realized that in order to get maximal performance out of these AI clusters, we needed to make some new decisions. Specifically, what we observed was that most of these AI clusters run on GPUs, and in order to get maximal performance, we needed to run these GPUs at their high thermal density point. Specifically, we found that for our H100 GPUs that were used for Llama, we needed to run them at 700 watts. When we take a bunch of these GPUs where individual GPUs consume 700 watts, pack many of them into a single machine, and then pack a few machines into a rack, we find that the rack exudes a whole bunch of heat, which requires that we think of our data center space in a different way to handle cooling, the new rack placement, etc. Right? So this spurs innovation at the DC layer. Next, we realized that in addition to the DC itself, we needed to ramp up on completely new network technologies in order to be able to interconnect these GPUs and then present an entire cluster abstraction to the software systems and all the ML engineers. In order to do this, we had to very quickly ramp up on RDMA and other technology. So specifically, what we realized at this point is that there are multiple solutions that are out there. There's Rocky, there's InfiniBand, and there's these other ideas. Now, the challenge here is we didn't quite know which solution worked best. We could obviously read about it, but we wouldn't know what is our experience like. So in order to solve this conundrum, we created two 24K clusters, one outfitted with Rocky, the second one with InfiniBand, so we could get hands-on experience and learn about the networking challenges, as well as how to make full use of this cluster. Again, as Joe mentioned, the Llama 3.1, all the Llama models, especially 3 and 3.1, were trained on our 16K Rocky cluster. Now, beyond the physical infra, at the software layer, we realized that we had to start innovating in a few different ways as well. Specifically, we needed to build specialized scheduling system in order to be able to schedule 16,000 GPUs to be able to run a single job. We also needed to figure out how to build out the operations muscle to get the maximal effective use out of this cluster. So let's dive into this next. So a key tenet of this Llama 3 training jobs is that they run on thousands upon thousands of GPUs. And unlike our previous ranking and recommendation AI jobs, we find that these jobs run for weeks on end, right? So we had to figure out how to build a custom scheduler. And then we had to figure out that in order to exercise this cluster well and get maximal performance out of it, we needed to leverage every resource element that we had. Specifically, we had to start off by pushing the capabilities of each GPU to their max within a single machine. We had to figure out how to get the most out of the multiple machines in a given rack. We had to figure out how to interconnect these machines into a small cluster of about 3,000 GPUs or so. And then we had to figure out how to interconnect these small AI clusters into a single large training cluster that we could use for a job the size of the Llama training run. We had to build all this complex machinery, and it's all shared in our mass scheduling system. And by the way, you can go read about mass online. Now, it wasn't just enough to build out this physical infrastructure, get all the GPUs in place, and then interconnect them. Next, we needed to also figure out, yes, we can schedule jobs on them, but how do we maximally get the performance of this cluster to be high? In order to do this, we had to figure out how to map different modes of algorithmic parallelism onto the hardware that we had. We accomplished this by taking tensor parallelism across GPUs in a single server. We then ran pipeline parallelism across racks in a small cluster. And then we leveraged data parallelism to make full use of the entire training cluster, right? So we had to put all these different pieces together in order to be able to push our cluster to its limit. Next, we also had to figure out how to keep the training job stable. This is easy to say, but really, really hard to do. Because what we have is we have 16,000 of these GPUs that have to be in tight interconnectivity, operating at a nanosecond pace, and really working together in a synchronized and coordinated manner for weeks upon weeks on end, right? And what we found was the training job would unfortunately come to a stop anytime there was a single failing GPU, anytime there was network congestion or communication issues across these GPUs, or there were any bugs in the software stack. This was really challenging and daunting when we started off. But what we quickly realized was that we had tons of experience from running production online systems. We could solve this problem by investing and extending our investments rather in observability and debugging and identifying ways where we could quickly identify failures at the hardware, network, or the DC layer, and then triaging these down. So we went about this work in two different ways. First, we leveraged a bunch of our software systems. For instance, we leveraged the flight recorder capabilities within PyTorch to capture every single communication event and its duration across the GPUs. Now, most of these would be held in memory. We would only dump them out anytime there was like a crash in the nickel watchdog timer or a heartbeat issue or something else, right? So we started getting telemetry and so on. Next, we invested in custom tools that allowed us to visualize performance issues. For instance, I developed a tool that allowed us to quickly debug slow collective communications and identify if the problem was at the communications layer or something going on in the compute kernels or in the hardware itself. And then these tools allowed us to quickly trash problems and then recover. The key takeaway or the key benefit of our observability and debugging investments was that we were able to achieve a 90% effective training time for our Llama 3 job. This was one of the most interesting things that I feel we learned through the Llama experience, and we're super proud to share this table with the broader community. So if you go to the Llama 3 paper, you can see it in gory detail. What you'll find is after running our job for a 54-day period, we ran into about 419 issues, of which the vast majority of them, about 78% of them, were due to hardware issues. I'm super proud of this work because it wasn't just the case that we were able to figure out how to quickly ramp up and in 18 months, go from running jobs on really small numbers of GPUs to these thousands upon thousands of GPUs. But further, we were able to figure out how to debug problems and get insights that allows not just us to plan for the future, but also the broader community to understand the science and the challenges behind operating these large-scale clusters. Now, as we look to the future, we feel like we're going to go way beyond what we're currently operating at, right? We expect to build even larger data centers and even more physical infrastructure. In order to keep pace with the growth that we anticipate in the future, we're making several changes to our software stack. For instance, we're overhauling our checkpointing mechanism by realizing that at a larger scale, we need to be checkpointing possibly even more frequently, and hence, we need to invest in things like in-memory checkpoints, writing snapshots to flash, as well as writing out snapshots and checkpoints asynchronously to persistent storage. Similarly, failure at the scale is inevitable, so we have to recognize that it's not enough to just save state, but also to invest in recovering from them. So we're optimizing how quickly we can load checkpoints back into memory. How do we do things like initialize large jobs and invest in nickel initialization speedups, as well as figuring out how to work on container restarts for the containers that run these AI jobs themselves. But it's not just software that we need to invest in. We also need to invest in the physical infra. For instance, as all of you are probably aware, GPUs are in scarce supply today, and we anticipate that they might continue to be in scarce supply. Further, we expect that the scale that we need to operate at is going to continue to increase. So how do we make use of the larger power or the larger clusters that we have? Well, we might need to outfit it with different generations of hardware. So for instance, it might not just suffice to use H100 GPUs. We might have to invest in the next generation of NVIDIA GPUs, and if need be, even in the previous generation, like A100s. So we need to now make sure that we can operate training on heterogeneous hardware from the same vendor like NVIDIA. But in addition to this, we might also need to run hardware of many different types. So we might need to operate NVIDIA hardware, but we might also need to run our own custom hardware, which is called MTIA. And then we might need to run training in a heterogeneous manner across all these different hardware types. Later today, you'll hear from Joel Coburn and several others about MTIA, so look forward to those talks too. Finally, at a very innate physical space, what we find is that it is really, really hard to get power and to build a single humongous data center. we just expect to run the laws of physics in acquiring power, or maybe in connecting all the GPUs that we need to in a single homogeneous way. This brings up a new challenge. Unfortunately, the current training paradigm of expecting all the GPUs to be connected uniformly and then leveraging synchronous training might not work. So we might need to start investing in completely new research strategies, such as asynchronous training, which is only a research idea or research concept. We might need to figure out how to port that into a production environment. So we're starting work of that type as well. Overall, as you can tell, we feel like we're barely getting started. Over the past 18 months, we've accomplished a lot in figuring out how infrastructure can enable us to develop these Llama models and scale our training. Next, we'll hear from Charlotte about what we're doing in the exciting world of inference. We're super excited to collaborate with you on training, inference, and everything beyond.
All right, thanks, KV, for the great talk on training infra that generate the model for us to play with. I'm Charlotte, working on LM Inference Infra at Meta. In the next 10 minutes, I'm going to show you how we deploy Llama to real production. Meta launched LM-based applications since last Connect. We're doing everything for free. Many of you might know that LM inference is notoriously expensive to serve. The model is huge. The generation is iterative. Behind the scene of every LM response, like here, we probably run model.forward more than 50 times. That is because the generation for each token is conditioned on all previously generated tokens. Apart from product, we also have a lot of internal traffic that the user don't see, like synthetic data generation, knowledge distillation, rejection sampling. This offline inference workload is massive. To give you an idea, for Llama 3 ROHF, we have to process hundreds of millions of examples for rejection sampling. And we have to do that in a very short period of time, and for a few rounds. Fitting both traffic at scale and efficiently is very challenging. Let me walk you through our journey to make that happen. In a nutshell, this is the bin packing problem. You're feeding models onto hardware. We have a lot of models. That is because one LM application is backed by multiple LM inference calls. You got the main model for chat and a bunch of ancillary models for integrity, enrichment, reward, and everything else. We also get a lot of hardware from different vendors of different shapes. They are best at different type of workload because they supply different amount of GPU flops, HBM capacity, and bandwidth. To make an economic decision here, we really have to understand the system implications of the LM weights, preview decode operations, and KV caching. This is our problem statement. To start solving this problem, let's start by looking at our hardware boxes. Here, we got two hosts installed with H100. They got CPU to GPU, inter-GPU, and inter-host communication, all at different speed and bandwidth. It's almost like a mini distributed system that you are running into potential bottlenecks almost everywhere. Each GPU has 80 gig of HBM. I want you to really remember that number, and let's start fitting some models. Llama 3 8B, fitting one GPU just fine. Moving to 70B. That is too big for one GPU. We have to use tensor parallelism to partition the model weights across multiple GPUs on the same host. Moving to our 405B model. Wow, the model weights in BF16 is over 800 gig. This is bigger than 8 H100 cards, and we have to keep some space for KV caching. This means you have to figure out how to do FBA quantization, or you find AMD MI300, which offers bigger HBM. Or you go with interhost pipeline parallelism to further partition the weights. Over time, we realized that preview and decode demand very different system resources. Preview is more compute heavy, and decode is more memory bandwidth heavy. We can disaggregate them into different services. This also helps us to mitigate the long tail decoding latency because of the interruption from long prefuse, which help us to maintain the same latency SLOs with much fewer machines. Long context models are getting more popular this year, which really create a big problem for us. That is because the GPU compute scales quadratically with context window, especially for long context model. To give you an example, long context models are getting more popular these years. It really creates a big problem for serving. That is because the GPU demand actually scales quadratically with context window, especially for very long context models. To give you an idea, running preview on 70 model with 1 million token, it's gonna take a few minutes. It's basically impossible to utilize that in very real-time application. If you don't want to use any approximation, you can use context parallelism to partition at the context dimension to allow you to further replicate the preview nodes and throw more compute and make things faster. If you want to run a long context model on 405B in BF16, you will need a little bit more mix and match. Here, we're mixing 3 types of parallelism. You got an 8-way tensor parallelism, 2-way pipeline parallelism, 2-way context parallelism, and a 3-to-1 preview decode ratio. Pretty complicated, right? And we have more interesting design over there. And when we're coming up with this system, we have to keep in mind to really make them compatible with all of the model architecture we are supporting, including some multimodal ones, speculative decoding, all of our custom kernels and customer inference engine. All right, so far, we've only talked about how to build a system that can serve a handful of LM requests. Next step is to take that system to real production. What you will see in real production? Well, you get more moving pieces. Your input length changes. You got peaks, troughs, and spikes just like all online services. Comparing to a fixed benchmarking environment, your batch sizes are smaller and varies. Your sequence length also changes. The input to output ratios are also different. And you also have to update your models frequently. We realize the closer your workload gets to production, the more you lose from these theoretical flops. And this gap can be easily over 10x. What does that mean for us? Well, it's a lot of hard work on performance. We're building the system to automatically select the best serving options for different workload. A lot of time, we're also asking ourselves, can we step back from the inference box? That is when you start seeing the non-inference latency and you see the fleet-wide inefficiency, which is sometimes make a lot of those absolute 10% performance wins not really that appealing to us. One of the biggest opportunities that you wouldn't be able to do a great job by only heads-on working on inference box is the prefix caching. For chatbot application, we put chat history and prompts all in the request. The KV tensor from previous turns are already computed. That is obviously some room for caching, right? We are doing this since last connect. We keep a cache of KV cache on the host RAM, and we sticky route the request from the same session to the same host with consistent hashing. We also want to continuously improving the cache hit rate, and that means you want prompts that are more cacheable, and you want cache that is bigger. To make prompts more cacheable, we're working very closely with our product infra team to improve the prefix similarity for our prompts by co-designing how the multi-turn chat history management should look like. To make the cache size bigger, we are offloading the cache from RAM to flash to distributed caching system. Finally, let's try to hook up everything together. Put everything we built to real data center in front of real users in real time. Now let me bring back some of my fancy boxes previously. Imagine you're going to do allocation for all of that. It's gonna be pretty challenging, right? It's even more challenging because maintenance and hardware failures happen all the time, like KV also mentioned. Inter-host distributed inference require hosts that are physically closer to each other, which tends to fail together at the same time, and we don't like that for online inference service. Some of our workloads are preemptible, some are not. And you want to place your host in a few more regions, otherwise your network latency is gonna be longer than your inference latency. We are pushing a lot of infra boundary to solve all of these problems. We are building network topology-aware scheduling for online services, which is actually different from the one we built for training. We built deployment solver to deal with allocation and routing constraints. We keep evolving our auto-scaling, load balancing, and management for elastic instances with awareness of specific LM performance patterns. And lastly, we also have to abstract away all of these operating complexity from our product team. To wrap up, optimizing LM performance is all about optimizing compute time and data movement time. Building an LM inference engine is like building a distributed operating system. You are taking a very system-oriented approach looking at these model architectures, and we are solving problems like scheduling, memory management, optimizing communications, and accessing external resources. The product trade-off is also gonna be more complicated. Out of the 5 axes here, model quality, latency, throughput, cost, and reliability, you only get to pick 2 or 3 out of 5. There's no free lunch. We are continuously improving the maximum capability for all of our axes to get ourselves ready for the upcoming challenges, where we are expected to continuously drive down costs for more modalities, longer contexts, more agentic use cases. We're so excited to see so many innovative ideas in the LM inference efficiency area across academia and industry. And we are looking forward to building this strong and economic foundation with every one of you to be ready to run AGI in the future. Thanks everyone for listening. Now I'm gonna hand back to my colleague KV to share his closing thought.
Thanks, Charlotte, for that fantastic talk on inference and what it takes to serve a global audience on Meta infrastructure. As AI training continues to scale to larger clusters and even more interesting ways of training, such as multimodal training, we expect to run into new infrastructure and algorithmic challenges. Specifically, we're going to figure out how to do things like build even larger clusters, invent completely new ways of interconnecting the GPUs that power these clusters, maybe by coming up with completely new networking paradigms or network communication paradigms. And then we're going to need to figure out how to run our large-scale AI jobs, schedule them on all these machines, take faster checkpoints, and so on. But more importantly, we're going to need to figure out how to survive the even more complex failures that we expect to encounter at even larger scale. If we get all these things right, then we might have a stable training job, which is able to use the cluster well. And the end output of that is going to be a trained model. Today, as you heard from Charlotte, we do a bunch of interesting things in terms of getting the models together, figuring out how to push them out to our inference serving systems and such. But in the future, with even larger models, we expect that we'll need even more weights and even more biases. And what we also expect is that we can't really cut off individual models, and we might have to develop completely new paradigms like real-time updates of weights and publishing things continually. Equally importantly, we're finding that we need to deal with larger scale. And again, we now run into the challenge that we might not have a single hardware family to serve all these models. We might need to deal with this complex heterogeneous hardware deployment that's needed to serve our end users. And finally, we need to understand how the products use these models and understand how factors like latency affect the user experience. Because remember, our end goal is to make sure that people who are using our models can go about their lives and have a better experience. So we need to figure out how to serve our users well. As you can tell, we're super excited about all of our work on AI and the different aspects of scale, hardware, clusters, network, and so on that this encompasses. This is pretty amazing. We are super excited to collaborate with all of you. And equally importantly, we feel that it is super critical and important that we do this in an open manner. We plan to keep publishing all of our work in the open. We plan to keep releasing our models. We hope to keep working with the PyTorch community, as well as the Open Compute, Open Network, and other communities across our infra stack. Thank you for joining us on this journey.
Thanks to the Llama team for the insightful talk. We will now hear from Hagai Lupesco from Databricks with his talk about unlocking AI's potential through open innovation.
Hi, everyone. It's awesome to be here today at the AtScale event. My name is Hagai, and I lead AI platform engineering at Databricks Mosaic AI, where we help thousands of customers build AI-powered applications. Today, I'm going to talk to you about open innovation in AI and why I believe open innovation is a critical ingredient in unlocking AI's massive potential. So for the past 5 years, we've all been really bathing in the warmth of an AI summer, and it feels awesome. AI has been the talk of the day for the past couple of years at this point, starting with the tech crowd here in Silicon Valley, as well as tech communities across the world, and even across broader crowds. The search term AI is currently at an all-time high, and the trend we're seeing here suggests we have not hit peak popularity just yet. And with broad interest, we've also seen investments in the field picking up steam really rapidly. If you look at the chart here, Gen AI investments grew 9-fold in 2023 alone, reaching $25 billion. And over 1,800 new AI companies were founded in 2023 alone, up 40% from the previous year. Now, we're also seeing AI applications gaining real popularity out there. 70% of developers are reported to either be using or planning to use AI tools as part of their development process this year. That's according to Stack Overflow 2023 survey that spanned over 90,000 developers worldwide. OpenAI ChatGPT, arguably the poster child of generative AI, is reported to be the fastest growing consumer internet app of all times, hitting over 100 million users in just under 2 months. Another poster child of AI, Waymo, reported doing over 700,000 trips with public riders and no human driver in 2023 alone, doing over 7 million miles across San Francisco, LA, and Phoenix. But despite all the positive and warmth of this AI summer, we've all seen AI winters before, where it was not always so warm and friendly. If we take a look back, since Turing proposed the idea of thinking machines and McCarthy coined the term we all use today, artificial intelligence, that was done sometime in the 1950s, we've actually gone through cycles of AI boom and then bust. The first AI winter took place in the 1970s. Marvin Minsky was a Turing Award winner, the co-founder of MIT's AI Lab, and really a luminary in the field. Back then, publicly predicted that within just a decade, humanity will create a machine with the general intelligence of an average human. That prediction, alongside similar predictions of other experts in the field, set really high and probably largely unrealistic expectations, which were then not met, and that led to the complete decimation of AI R&D funding, giving us the first AI winter. We then had the second AI winter at the heels of a resurgence in AI R&D excitement, primarily around expert systems, which were designed to capture and encode human experts' knowledge and then allow the AI to apply that knowledge. Now, unfortunately, despite the hype and excitement, expert system turned out to be fragile, expensive and slow to develop, and then not really robust for changes, again leading to another decimation in R&D investments in AI and the second AI winter. Since then, we've gradually started seeing picking up with the internet taking over our lives, big data, machine learning. That winter turned into spring with the AlexNet deep learning moment of 2012, leading up to today's new Gen AI boom and AI summer, with generative AI really astonishing everyone with the capabilities for text generation, image generation, speech generation, and even video generation. But if we take a look back, both AI winters came at the heels of really high expectation and excitement that then were unfortunately not met. Now, I personally experienced the impact of the second AI winter as a young software engineer early in my career. I was just out of graduate school where I built expertise in computer vision, joined an exciting startup building AI systems for automated detection of defects in electronic components. That work was super exciting, very challenging. The picture on the left shows the younger version of me, and that refrigerator-like device with a traffic light sticking out was a sophisticated system comprising of robots, actuators, special lighting, special cameras, and of course the crown jewels, sophisticated computer vision and machine learning algorithms. Now, despite the technology we've built being AI-powered, we were intentionally careful back then not to brand our company, products, or technology as AI. We're still experiencing the AI winter, and AI was frowned upon and would not help us land customers nor investments. And most other companies in our industry, just like us, fiercely avoided mentioning the term AI at all. That was the impact of an AI winter. Now, with all that said about the past and present of AI, the interesting question is, what will be the future? If you look at the technology hype cycle model, which was developed by Gartner, it actually offers an interesting mental model for the maturity and adoption of new technologies. And many, including myself, believe that that model applies largely to AI today. Now, almost 2 years ago, powerful AI demos such as ChatGPT and Stable Diffusion came online, blowing people's mind with what modern neural network-based AI is capable of. That was Gen AI's technology trigger moment on the lower left corner of that chart. I would argue that today we are at the peak of expectations. Some of these expectations may indeed be inflated, some may be real, and we're definitely seeing a lot of FOMO, fear of missing out, on the investment community that is pouring a lot of money into the field. Now, the interesting question is, going forward, will we hit the trough of disillusionment? If we do, how hard is it going to be? And what is our path towards a plateau of productivity and a future where AI is successful? So, what does it take for us to sail towards a future where AI is ubiquitous and successful? I want to offer 3 key requirements for AI's future success. The first one is that we shift gears. We move from being model-centric to being system-centric. Those of us who have tried to build and deploy a real-world, production-grade AI application know that the AI model, is just one piece of that puzzle. It's an important piece. It's just one piece out of a few pieces that need to work together within an AI system. Next, we need more capable foundation models. Foundation models are the backbone of any world-class AI system. And while models such as Llama, Gemini, Claude, or GPT, they really have gone a long way in recent years in terms of their capabilities, there's still a lot of room for growth for things like multimodality, context length, multilingual support, reasoning, tool use, and this is just naming a few of the gaps. And then, last but not least, cost efficiency is a critical requirement for AI success. As long as the cost of serving AI models and systems remain high, the economical viability of AI applications remains very limited. Now, with these requirements in mind, I'd like to share a hot take. My hot take is that open innovation is the key ingredient for AI success. It's going to enable all these requirements I mentioned earlier and many others and even accelerate them. Now, what does open innovation mean? It means publishing AI research. It means open sourcing code for models and AI infra. It means making model weights and training datasets available for the community. There are other important ingredients for AI success, of course, but open innovation is arguably one of the most important ingredients that is an enabler for many others. Let's dive into this hot take. Starting with shifting our thinking from AI models to AI systems. At Databricks, we work with thousands of enterprise customers, many of which are actively building applications leveraging AI. Now, we talk a lot to our customers and we learn a lot from them. And a couple of months ago, some of my colleagues at Databricks, together with academics, published a blog post sharing an important observation after talking to thousands of customers. That observation is that it's AI systems, much more than just models, that are required in order to build world-class applications powered by AI. Now, a few key examples for great AI systems available today include popular consumer as well as enterprise applications, OpenAI ChatGPT, Microsoft Bing, Perplexity, as well as an AI product very popular by Databricks customers, the Databricks Assistant. Implementing each one of these AI systems, as well as many others, is very complex and hairy. It requires implementing design patterns such as RAG, retrieval augmented generation, multi-step LLM chain, function calling, tool use, to name just a few. Now, luckily, we've seen massive innovation coming out of the open source community and academia with open source tools that enable building, evaluating, optimizing, and deploying AI systems quickly and reliably. To name just a few of the key open source projects out there for that: LangChain for LLM chains, Llama Index for data ingestion and indexing, AutoGPT for building agents, DSPy for end-to-end system optimization, Milvus for vector search, and again, the list goes on. Each one of these projects has been used by tens of thousands of developers and counting. What's even more beautiful is that each one of these projects has been developed by hundreds of developers, sometimes even thousands, across companies, countries, and continents. Together, the community is building tools that enable the community itself to build better tools and better AI systems. Now, moving over to the second requirement, the need to have highly capable foundation models. Here are some of the top AI models built in the last couple of years. Each one of these models is highly capable in complex tasks for language and image understanding and generation, and really each one of these models helped pave the path for AI. But these models have another important thing in common. Each one of these models was made possible thanks to open innovation, thanks to open research, other open models, software libraries, datasets, as well as openly shared knowledge. Two highlights of open innovation enabling these models I'd like to make is, first of all, the Transformer architecture, which is open research published by Google researchers back in 2017 in the famous Attention is All You Need paper. Second is PyTorch. PyTorch is today the backbone of the vast majority of AI models out there today. Without these two open innovations, as well as many others, we would have likely moved much, much more slowly on the path to develop state-of-the-art AI. An anecdote of the importance of open innovation for progress in foundation models is my own personal experience training DBRX. DBRX is a mixture of experts, or MOE, model we trained at Databricks, which at the time of release was one of the best open models out there, and it got us and the model a lot of both community and media attention. Building DBRX was done in a relatively short amount of time, was a very tall order. It would not have been possible without PyTorch as the backbone for the model architecture, training, and deployment. And even more so, it would not have been possible without a very close collaboration we were fortunate to have with the PyTorch team. Open innovation also means we contribute our work back to the community. And so we open source DBRX. We contributed back to projects such as PyTorch, Megablocks, LLM Foundry, and others. And we also sat down with the PyTorch team to write down our learnings on training mixture of experts model and sharing these learnings back with the community in a detailed blog post we've published together. Now, we've seen many new MOE models trained subsequently, benefiting from this open innovation. This is exactly the power of open innovation, that it builds on top of other open innovations. Now, thanks to this open innovation, we now have a rich ecosystem of open foundation models that are just as good as closed models. If you look at the chart here, it's exciting to see clearly, first of all, how much AI has progressed over just the last couple of years. Just look at that y-axis to see how much models have gotten better in this short amount of time. The other very exciting thing to see is just how much the gap between closed and open models have gotten smaller, and I expect this trend to continue. Now, all of these models we just discussed are extremely computationally intensive and hence extremely costly to deploy. How computationally intensive and how costly? Let's take as an example the new Llama 3.1 4 or 5 billion parameters, one of the best LLMs available today. Let's just look at what it takes to deploy the model for inference. Now, the model has 405 billion parameters. And assuming we're deploying it with an optimized 8-bit per parameter, it's going to take us about 405 gigabytes of memory on the GPU for inference. Now, considering the compute requirements, an LLM forward pass, that's a basic inference operation that generates the next token, that requires about 2 flops, or floating point operations, for each model parameter to predict the next token. This means generating a single token requires about 810 gigaflops. to deploy it, we need a strong GPU, and we might go for the NVIDIA H100 GPU, one of the best GPUs available today. Each one of these GPUs has 80 gigabytes of RAM. So to deploy this specific model for inference, we need about 8 H100 GPUs, giving us 640 gigabytes of GPU memory and just enough compute petaflops, about 16 petaflops, to allow us to generate about 2,000 tokens per second. Such a deployment is going to set us back about $50 per hour on one of the major cloud providers out there. That comes out to a pretty hefty cloud bill of just over $400,000 a year. And this is just for one deployment that will get us about 2,000 tokens per second, roughly equivalent to handling a load of about 1 request per second. Just imagine the cost of deploying this model for prediction at scale. Again, luckily, and thanks to the open innovation, there are many impactful initiatives in the AI research and open source communities that are targeting this specific challenge of efficient AI deployments. I've highlighted a few projects here. There are definitely hundreds of others, from Flash Attention, Medusa, and DeepSpeed out of the open research community, through Hugging Face TGI, VLLM, and others on the open source community. Each one of these projects is tackling the problem of cost-efficient deployment at scale. One open innovation project I'd like to highlight is SGLang. SGLang is an open source project with the mission to enable fast and efficient serving of large AI models. SGLang leverages open research with things like Flash Attention, Radix Attention, Torch Compile, SLoRa, and many others. What's interesting about SGLang is open research built on top of open research. And as you can see on the chart on the right, it actually delivers state-of-the-art performance for serving models even as large as the Llama 405B we discussed earlier, offering best-in-class throughput as well as latency. Okay, we're at the end of the talk, and if you'll take just one thing out of this talk, I'd like it to be that open innovation is key to AI's future success. And why is that? First, it helps us build better AI systems and better AI models. Second, it enables deploying AI efficiently and at scale. And third, and probably most importantly, it accelerates AI development through code reuse, knowledge sharing, as well as open collaboration. And with that in mind, I wish all of us to continue enjoying a long and warm AI summer filled with open innovation. Thank you for your time.
Thank you, Hagai. Continuing with the theme of open innovation, next is the PyTorch team, kicking off with Juan Chao, followed by Evan and Kamish.
Hi, everyone. My name is Wan Chao Liang, and I'm an engineer from the PyTorch core team, working on distributed training. Today, we're going to talk about PyTorch and large language models. PyTorch has been playing a critical role in the AI evolution and the entire life cycle of large language models. Researchers and engineers could quickly prototype transformer models, build efficient tools from model pre-training, post-training, to fine-tuning and inference using PyTorch. The open source community has built a wide range of tools using PyTorch to push the boundaries of large language model capabilities. Open source innovation that is happening across the world contributed significantly to the AI evolutions. At Meta, we greatly value open source and believe that open innovation could lead the AI models be safer, more secure, and efficient. To further enable the ongoing research of transformers in the era of large language models, the PyTorch team also started many efforts to help accelerate the AI evolutions and enrich the open source ecosystem. Starting from large-scale training, the PyTorch team has been building many training algorithms through improvements to PyTorch, for example, n-dimensional parallelisms. To make fine-tuning a pre-trained model more accessible, we have implemented memory-efficient training techniques and fine-tuning techniques through new open libraries like TorchTune. We have also built out muscles to deploy models on different devices via Execute Torch, run efficient inference via GPT-Fast, making large language models be openly accessible everywhere. We'll walk through each of them in today's talk. Next, let's talk more about large-scale training with PyTorch. The industry invested heavily into large language model pre-training. What is special about pre-training and why it requires foundational investments? Today, pre-training imposes lots of technical challenges. First, model size grow exponentially over the past few years. Today, many large language models ranging from 7 billion parameters to more than trillions of parameters. Second, huge amount of data needed. Data size also increasing crazily where trillions of tokens are needed in order to get great model quality. Given the large model size and huge amount of data, the training would take millions of GPU hours or hundreds of years to finish. So we need a robust large-scale training system that could scale the model training to tens of thousands of GPUs, staying training efficient and converging as if we are training in a single device. This requires many innovations, from hardware level to software level and many system level optimizations. Within a robust large-scale training system, distributed training becomes critically important. The PyTorch distributed library offers a wide range of tools to build such a system. We have Torch Run for launching distributed training jobs in cluster. We offer communication primitives where a user could call collectives like allReduce, allGather using beacons like Nico. Parallelism primitives. We built out dtensor to express tensor-level sharding and device mesh to express multidimensional communicators in the context of n-dimensional parallelism. These primitives together enable the system developers to build efficient training solutions that could scale their model training for different use cases. On top of these primitives, PyTorch Distributed also offers end-to-end parallelism solutions, including our popular data parallel solutions, distributed data parallel, fully sharded data parallel, and the model parallel solutions, including tensor parallel, pipeline parallel, to further scale model training to thousands of GPUs. For instance, we have been collaborating closely with Databricks and IBM team on parallelism solutions. Our solutions empower Databricks to scale the mixture of experts training to 3,000 GPUs using hybrid sharded data parallel and dtensor. For production training, PyTorch Distributed offers an efficient checkpoint save and load solution to support long-time training with fast failure recovery. Our collaboration with the IBM research team yield over 10 times improvement for model checkpointing time. Apart from distributed algorithms, there are many other important training techniques that could further scale and improve the training efficiencies. To name a few that PyTorch provides: activation recomputation, a technique that could save the memory during forward by recomputing activations again in the backward. Mixed precision training recipes, where it allows training with lower precision D types and keep convergence. This could not only save the GPU memory, but also improve the training efficiency. Torch Compile. We introduced a compiler stack for PyTorch models since PyTorch 2.0. Torch Compile could improve training performance without changing the model code. It provides the capability to fuse computation operations and perform communication optimizations. All of these techniques could further improve the training performance. So you may wonder that there are so many training algorithms and techniques needed for efficient pre-training. How could developers actually use them all together? To demonstrate end-to-end training with those techniques, we're introducing Torch Titan. Torch Titan is an open source proof of concept for large-scale training with native PyTorch. Torch Titan is built with PyTorch design principles, focusing on simplicity and ease of use. It implemented three-dimensional parallelism training for transformer models, including fully sharded data parallel, tensor or sequence parallel, and pipeline parallel. It showcased how to compose many efficient training techniques together in a simple manner, allowing extensibility across software components and achieve great performance. For example, users could easily configure their selective activation recomputation policy for memory saving. Turn on torch compile to enable compute fusion. For H100 and above GPUs, user could enable IPA training to improve the T-flops. Furthermore, the checkpoints saved in Torch Titan can be easily converted and loaded into TorchTune to start fine-tuning with custom data size. Now, wrapping up large-scale training, we're expecting model size and number of GPUs continue to grow. There are so many exciting challenges ahead of us that we're working on right now. To name a few, fault tolerance and fast restart. This become critical as node failures become very common at large scale. Preserving debuggability across our software stack is essential for failure root cause. We also want to continue improve training efficiency while keeping power constraint in mind. As we are heading towards multimodality large language models as the first-class citizen, we need to tackle new challenges that may be different from text-only large language models. We still want to preserve the interoperability into fine-tuning and inference. Solving these challenges are both exciting and critical for the future. Next, I'll hand it off to my colleague Evan, who will talk about fine-tuning for large language models. Thank you.
Thanks, Wanchao. Hi, my name is Evan Smothers. I'm an engineer on the PyTorch domains team, focusing on fine-tuning. I'm going to talk about fine-tuning large language models using PyTorch. We can think of the different stages in the lifecycle of large language models as a funnel. The large-scale training discussed by Wanchao sits at the top of the funnel. It requires the most memory, the most compute, and as a result, it's generally the least accessible. At the bottom of the funnel lies on-device inference. Here we run distilled or quantized models locally with minimal memory footprint. These models are broadly accessible, since anyone with a smartphone can use them. They also tend to be tailored to specific applications. Fine-tuning sits in the middle of the funnel. It's the means by which we bridge the gap between large pre-trained models and efficient on-device inference. While LLMs are pre-trained on massive corpora of data, there are actually a lot of tasks that they're not especially good at. One very common example would be math problems, where pre-trained generalist LLMs perform notoriously poorly. One goal of fine-tuning is to turn generalist models into specialist models. This is often informed by whatever the task of interest is. For example, maybe you work in a radiology lab, and you want a model to summarize radiology reports. This is an example of both domain and task adaptation, the domain being the medical domain, and the task being summarization. Common response to, my model is not good enough at task X, is to use a bigger model. As we'll see in the next portion of this talk, this is not always an option. If we're going to deploy our models on device, we need them to be lean. This is really the essence of fine-tuning. Given a task and a desired memory profile, what datasets, modeling methods, and training techniques can we use to maximize our model's performance on the task, subject to said memory constraints? LLMs are often pre-trained on whatever the latest state-of-the-art hardware is. But many fine-tuners, such as those in the popular subreddit r/local llama, only have access to a couple of older generation GPUs. We can do some quick math here. Most open source LLMs fall somewhere in the range of 1 billion to 100 billion parameters. If we store all of our weights in half precision like bfloat 16, that's 2 bytes per parameter. If every parameter is trainable, that's another 2 bytes per parameter for gradients. If we use an optimizer requiring momentum like Atom, that's another 4 bytes per parameter. Adding that all up, even a smaller model like Llama 2 7B would require 56 gigabytes of memory, putting it out of range of many consumer-grade GPUs. This is not even considering larger models like Llama 3 70B, where the parameters alone will require multiple 80 gig GPUs just to store them. On the other end of the spectrum, many people rely on Colab for free-tier GPUs. These have 16 gigabytes of VRAM and no bfloat 16 support. In that case, even just storing all of the Llama 3 8B weights in half precision will cause an These very different hardware profiles necessitate a range of different techniques for memory efficiency. The objective of supervised fine-tuning is basically the same as free training. It still uses next token prediction. One of the biggest changes is around the scale of the dataset. This means that it's relatively cheap to launch a bunch of concurrent fine-tuning experiments. And so ease of experimentation and ability to get quick feedback on model performance become really important for fine-tuning workflows. Common paths for getting these signals include evaluation on academic or custom benchmarks for model quality, or more qualitative evaluation via text generation. Once a model is fine-tuned, it's also common to quantize it to further reduce the memory footprint. We'll see more on this in a bit. Finally, there are a lot of solutions out there across fine-tuning, evaluation, quantization, generation. It's not always easy to convert a fine-tuned checkpoint from framework X into one that can be quantized by library Y. More importantly, there are often many layers of abstraction wrapping the actual training code. Researchers and practitioners alike often want to tinker with the particulars of the training loop. It's not always easy to do that in the existing solutions. To address some of these challenges, we've released TorchTune, a library for easy and transparent fine-tuning of large language models using pure PyTorch. TorchTune onboards the latest and greatest techniques from both PyTorch and the broader ecosystem to make fine-tuning more accessible across a range of different hardware setups. TorchTune provides simple and hackable training recipes that can be copied and modified right from the command line. We give users direct and transparent access to the training code. This makes it easy to try out new techniques. We've had new recipes like quantization-aware training or multiple alignment methods onboarded to our library just by modifying our existing recipes. Our core library consists of modular building blocks that can be easily swapped out for quick experimentation. We provide model builders for easy one-liner access to canonical implementations of state-of-the-art models. Say you want to onboard some new attention technique. You just need to write the class, build it in one of our existing models, or write your own, point the training recipe to it from the command line, and you're off. We provide interoperability with the broader ecosystem via integrations with Hugging Face, Weights and Biases, Eleuther's evaluation harness, and more. We partner closely with the open source community and have received community contributions onboarding DPO and PPO training scripts, Llama, Qwen2 models, and more. Our checkpoints can also be exported for inference with ExecuTorch. TorchTune leverages tools and techniques from the broader PyTorch ecosystem to increase the accessibility of fine-tuning. We support low-precision techniques like full bfloat16 training or reduced precision optimizers. All the standard memory-saving techniques like CPU offload, activation recomputation, or gradient accumulation are supported directly via the canonical PyTorch APIs. Other, more specialized techniques like fusing optimizer step and backward or sample packing are also available, and we demonstrate them transparently in our single-file training scripts. One of the most common ways to improve memory efficiency is via parameter-efficient fine-tuning, where the majority of model weights are frozen and smaller trainable adapters are inserted to save gradient and optimizer memory. We provide simple training scripts for LoRa and QLoRa, and we leverage the latest PyTorch distributed APIs to support fine-tuning of Llama 3 70B on two 4090s via QLoRa and Torch Compile. Finally, we provide details of peak memory and tokens per second on different hardware setups for all of our training scripts directly on our README. Looking forward, there are a lot of things to be excited about in the fine-tuning space. Language models are becoming increasingly multimodal, with an ability to intersperse image, video, or audio data as context for the language model. This will make memory efficiency even more critical for fine-tuning. It will challenge fine-tuners to find new ways to apply adapters or shard their models for distributed training. Multimodal signals don't have to be restricted to only inputs. With agent-based LLM workflows, we can even call image generation models as part of our inference flow. These are just a couple examples of some exciting techniques around multimodality that are on the horizon. Next, I'll hand it off to Kimish to talk more about what we can do with our fine-tuned models, some of the big technical challenges there.
Thanks, Evan. Hello, my name is Kimish Patel, and I'm a software engineer in PyTorch Edge team at Meta. Today, we will be talking about enabling on-device inference of LLMs. So far, we talked about leveraging large-scale distributed infrastructure to train LLMs, and subsequently using smaller setup with single-node GPU to fine-tune pre-trained model for a specific use case. In continuation of that, In this part of the talk, we will talk about deploying such a fine-tuned model on a constrained device for inference. A fine-tuned model can be deployed across many surfaces, such as server-side inference that provide LLM inference as a service, or local inference, where the model or service is run locally on device, which may include laptop or desktop with local GPU, smartphone, AR/VR devices, or embedded devices. Given the large-scale nature of LLMs, one may naturally ask, why are we even doing local inference? Well, local inference provides users to trade off capability of a very large general model against task-specific, relatively smaller model that can be deployed locally for privacy, latency, cost, and other reasons such as available data bandwidth through carriers or internet providers, which may vary significantly across different geographies. However, enabling large-scale models across these surfaces have significant challenges, since these models require significant amount of memory and compute resources, and we have limited amount of those on our target for deployment. For example, on high-end laptop or desktop, you may have tens of gigabytes of RAM, while even high-end phones may have somewhere between 6 or 12 gigabytes of RAM. This gets further accentuated when we go to wearables, which may have 1 to maybe 2 gigabytes of RAM. Available power due to lack of active cooling also varies significantly across the spectrum. Furthermore, modern SoCs contain wide variety of task-specific accelerators such as GPUs, neural engine, image processing blocks, etc. These constraints throw some challenges for deployment. For example, limited on-device memory means we must reduce the model size. Not only that, if we have different use cases such as message summarization or smart compose, each such use case cannot ship its own large model due to limited memory and disk space. Furthermore, we must make sure these models run efficiently to meet the latency requirement, which in turn means we must figure out how to leverage the available hardware to the maximum. Let's take a look at how we can address each of these challenges. Techniques such as quantization and sparsity help reduce model size. Quantization enables us to compress information into fewer bits by leveraging redundancy. However, many of the large models are dense in information despite being large in size. This has resulted in more innovation in the field of quantization, where new algorithms like HQQ, GPTQ, SpinQuant has enabled low-bit quantization. Pruning and sparsity is another technique that relies on neuron density, meaning leveraging those parameters that are more important than the others and pruning the other ones with relatively less information. While quantization and pruning help reduce model size, it may not be sufficient if we have to deploy entirely separate model for every on-device use case, such as message summarization or smart compose. Low-rank adapters allow us to deploy one model with different adapters for different use cases, and thus still allowing us to leverage single foundational model. Furthermore, we must run these models efficiently to meet latency requirement. These models are heavy both on memory bandwidth, meaning how much memory do I need to read to run one iteration of inference, and on compute, meaning how many operations do I need to do to run one iteration of inference. And each deployment surface has a limited amount of those. We have to ensure that we are able to leverage these resources maximally using efficient kernels for matrix multiplication, attention, which are the workhorse of these models. Okay, so we talked about the solutions we can employ to address these challenges. Let's see how PyTorch enables these solutions. Torch.io is a PyTorch library where we are working with community to enable low-bit D types such as int4 or FP6 and quantization schemes such as GPTQ, HQQ, as well as providing pruning APIs. Using these APIs, you can quantize a large model to 4-bit or 3-bit D types. TorchTune, that was introduced earlier, allows us to fine-tune small-size adapters. And for executing models efficiently, PyTorch ecosystem provides two solutions. Torch Compile, which generates efficient code for backends such as GPUs and CPUs by doing, among other things, aggressive fusion to reduce memory bandwidth requirement. On the other hand, ExecuTorch, which is a very lightweight runtime with first-class support for leveraging on-chip accelerator, like Apple's neural engine via its delegate interface, is well suited for deployment across phones or embedded devices. Both Torch Compile and Execute leverage native graph capturing technology, export. Exported graph can be shape specialized or can support dynamic shape via symbolic shapes. Such graphs then form the basis for the rest of the stack. In the case of Torch compile, it can be inductor plus Triton. Inductor's Triton backend provides lowering for various ops in Triton language, which gets compiled into Kuben. On the executor side, once the graph is captured, entire graph or parts of the graph can be relegated to specialized backends. For example, to leverage Apple's neural engine, we can use core ML or MPS delegate of executorch to lower parts of the graph to be executed on the neural engine. All right, so today we talked about the challenges involved in extremely large-scale training, efficient fine-tuning, and then performant inference for large language models, whose size range from hundreds of billions of parameters to a few billion parameters. But our story doesn't end here. This is just the beginning of generative AI's capabilities as we add more modalities besides text to models' learning capacity. Such modalities include vision, speech. You can imagine the growth in complexity across our stack to support these modalities. Meta is well positioned to take on these challenges to leverage generative AI capabilities across its products, including family of apps and reality lab devices. And we are committed to do this in an open ecosystem. These are exciting times both for the use cases that AI will spawn and the challenges we will have to tackle to enable them. Thank you.
Thanks to the PyTorch team. It's exciting to hear about all the open innovation. Next up, we'll hear from Meta's co-design and hardware team.
Welcome to our presentation today. We're going to talk about MTIA, which is Meta's in-house training and inference accelerator. We'll talk about how we've co-designed our models to give us high efficiency for inference workloads in the data center. I'm Joel Coburn, along with my colleagues Junxing Lan and Jack Montgomery, and we're going to take you through the model co-design process on MTIA. I'll briefly talk about model co-design. Junxing will jump in and talk about silicon architecture, how we've customized it for our models. Jack will talk about the software stack and the developer ecosystem. And then I'll wrap up by talking about some end-to-end results and future directions for our accelerator program. So now let's jump into model co-design. I want to start by taking a look back at last year's Scale talk, where we introduced MTIA and talked about these three pillars of a successful accelerator program. First, we focused on the end result. So the goal with MTIA was to improve user experience for applications like Facebook, WhatsApp, Instagram. And we do that by providing more accurate, interesting predictions, increasing watch times, click-through rate, etc. And that all comes down to our ML models. And using MTIA, we can provide better developer efficiency and better perf per TCO to deploy them in the data center. So on the developer ecosystem side, we've created full PyTorch support for MTIA to provide a familiar developer experience. And we'll talk more about that later, as well as Triton support for kernels. And all this helps to solve the programmability challenge in any accelerator. Then we've also focused on the design process so that we can design the chip and the system to give us the best perf per TCO, but then also we could minimize the time to market so we could get to market quickly, because the competitive landscape is very difficult for accelerators. And we did this by leveraging open source components, vendor partnerships, leveraging third-party IP, and then we could focus on designing the custom logic for the key parts of our models where we could get higher efficiency. So with that in mind, let's look at some model trends now that are really driving adoption of MTIA. So we focused on the ranking and recommendation space, and particularly in late stage ranking, we've seen an increase in model complexity and model size over time. The graph on the upper right shows that as we increase the gigaflops per sample, we continue to improve the accuracy of predictions with the model. So that means there's still value to scaling up the model. At the same time, we have this challenge where we have a really broad set of applications and a huge range of models to serve them, as much as 60x gap in complexity and size. We also are seeing a lot of accelerator demand for early stage ranking. This is where we do retrieval and ranking of a large number of candidates for the late stage, and the models tend to be very low complexity and high throughput. And then finally, we see a trend toward Gen AI techniques for recommendation models. So this is even more demand. So sequence-based models with transformer-like architectures can provide better prediction quality here. For example, the HSTU architecture at Meta does this, but it has over 10x increase in complexity and model size compared to our state-of-the-art late-stage ranking. So now let's look at the silicon and the system and choices we made to co-design it for our models. So on the silicon side, one key choice was to build the chip with a very large SRAM cache for holding activations and caching embeddings. This makes our models much more efficient. It also was a key decision because it allowed us to also pick LPDDR for off-chip DRAM as opposed to HBM, which many accelerators have today. And it turns out we don't need it here because we don't need as much off-chip memory bandwidth. LPDDR is lower power, it saves us money, but interestingly, we have to deal with doing ECC inline, which costs us some performance, but it is a worthwhile trade-off here. We've also built several offload engines in the hardware to accelerate sort of the most expensive operators in our models. So dot product engine for gens and SIMD units for activation functions and embedding pooling. We've also explored numerics and model compression by supporting types like FP16, int8, int4 that are particularly prevalent in our ranking and recommendation models. Another thing we've been able to do is really customize the ratio of flops to memory bandwidth, to memory capacity, and to I/O bandwidth with the host. And that's something that's much more difficult to do in a third-party solution. And then finally, with our knowledge of the serving stack, we've been able to optimize the system design so that we really get the right balance of partitioning the models between CPUs and accelerators. And that's led to a much denser system design. We have 24 ASICs connected over PCIe and a dual socket CPU. And this gives us much higher perf per dollar and perf per watt. So now let's consider the PyTorch ecosystem and what that means for MTIA. So we've provided PyTorch to give us a familiar developer experience, all of the features that developers are used to. And we've adopted it also to support PyTorch 2.0, where we can get things like Torch Inductor and Torch Dynamo to basically support the demands of new models and efficiently map our operators to MTIA and to other backends. And then finally, on the kernel authoring side, we've added support for Triton. So you can write the same kernel that could run on a GPU, CPU, or an accelerator like MTIA. And Jack will discuss all of this later. So finally, I'd like to share a comparison between MTIA v1 and MTIA v2. Compared to the chip we announced last year, our v2 design is much more powerful. And this was one of our main goals. We wanted to be able to have it be more capable to serve even larger models to improve our applications. So a few things I'd highlight. We have 2x more on-chip SRAM, which improves our performance. We doubled the LPDDR off-chip to serve larger models. We've increased the on-chip SRAM bandwidth by 3x, and we've done that really to feed 3x more peak flops, which allows us to serve those more complex models. The v2 design is very competitive in terms of absolute performance at a rack level with our baseline deployed in the data center, and it's capable of handling these larger models with significant perf per dollar savings. So now let's dive into the silicon architecture, which Chunxin will talk about.
Thanks, Joe, for the introduction. I'm going to switch to the MTIA accelerator itself. Hi, everyone. My name is Junqiang Lan. I'm an architecture lead from the Infra Silicon team of Meta. AI and its applications can significantly change the world and our lives. The active triangle of ML model, data, and computing resources are the three main driving forces of the AI wave today. It is our great pleasure to contribute from the computing side and share the updates on MTIA silicon development. MTIA stands for Meta Training and Inference Accelerator. It is customized designed processor for Meta AI models and workload. The overall better power efficiency or perf per watt as target in mind, the so-called next generation accelerator is a continuation of the previous generation we unveiled last year. In my section, I will give an overview of the chip, then explore the architecture a little bit. Then I will focus on the unique optimizations specifically for our own model and applications. Lastly, I will share the future direction of the MTIA program. The next generation accelerator has been landed in our data centers and started serving real traffic. The chip was taped out with TSMC 5nm process. The plan on record targeting frequency was 1.1 gigahertz, but with the margins from solid backend time enclosure and also thorough characterization from the lab, we were able to boost it to 1.35 gigahertz, which gives us 20+% performance boost. It is a complicated ASIC with 2.35 billion gates on the die, but as you can see, the silicon in my hand. In the world of AI accelerators, this is already a moderate-sized chip with total power of 90 watts. Let's take a closer look at the architecture of this generation. You can see we have the same 8x8 compute grid as the previous generation with more balanced NOC or mesh networks. Each PE again consists of CPU control cores, dedicated matrix multiplication engines, and special math engines. We also support SIMD or DSP-like vector extensions for generic programming. We made significant improvement on the computing, which is the key metric for AI acceleration. We achieved 177 teraflops on FP16 and BF16, which is 3.5x over the previous generation. On the integer support side, int8 and int4 are 2 times, 4 times the number as the floating 16-bit. On the memory hierarchical, we increased on-chip SRAM, increased DRAM size, we increased the bandwidth to just have a more balanced computing and memory. Besides the power and TCO or total cost ownership benefits, the reason that we are going with in-house design is to have a better vertical integration all the way from our model to accelerator hardware design. Here are a few examples. We achieved higher computing, as we mentioned in previous slides. We supported sparse matrix multiplication and yield more effective T-flops by ignoring the zeros. The weight is further compressed by asymmetric number system or ANS algorithm. This saves bandwidth and also have better power performance. We also optimize the mesh network so that the compute and data movement are more balanced. And the 3 detailed optimization I'm going to dig a little bit deep is for small precision integer int8 quantization, dynamic quantization support, PyTorch eager mode, and also the table batch embedding optimization. Let's dive on these optimizations one by one. Quantization is common to convert data to lower bits precision for fast or efficient gen in the next layer. The exact dynamic range of data is collected in MTIA post-gen, and the quantization parameter is most accurate compared to static quantization. Channel-wise dynamic quantization is built in. So this brought us a less than 0.05 loss or normalized entropy difference to compare with the 32-bit floating point numbers with very high accuracy. PyTorch eager mode requires immediate execution. Direct way of host to launch a job is to do a command copy, interrupt to PE through IPC. P and CPU reads the job descriptor. The interaction between CPUs brought long latency. In this generation, special hardware blocks are added to broadcast working queue to PE. PE then use DMA to read the descriptor so that the CPU is offloaded. This brought the whole job launch time to 20%, only 20% with previous generation. Table batch embedding is one of the most important optimization on inference in ranking models. As MRS, we specifically built hardware features to accelerate TBE. We added new hardware instructions. We support rotate DMAs. Multiple contexts unrolling is also supported. We also add the compression engine to alleviate large embedding indexes to load from host to the P side. We achieved 2 to 3 times faster than previous generation on TBE operations, and we also achieved 30%, up to 30% SRAM flying bandwidth. Successful landing on silicon into production is not an easy goal. It is a multi-year planning, flawless execution, and close interaction among multiple organizations and teams. Great thanks and big applause to all the cross-functional teams to make it happen. The chip is now running real workloads with a better proof per TCO. This journey is 1% done. we're looking into some of the most exciting improvements as listed on the slides, including the obvious more computing, higher efficiency, multi-device collaboration via collectives, GenAI, large language model specific optimizations, as well as more meta-only workload support. Please stay tuned for more silicon updates down the road. Next, I will pass to Jack to talk about software optimization on MTIA. Thank you.
Thanks. My name is Jack Montgomery, and I'm going to talk about what we've been working on in the MTIA software stack. In this section, I'll share 5 main ideas about MTIA software. First, the principles and goals of the software stack, PyTorch integration, kernel authoring with Triton, support for new features and model types, and finally, scaling model performance. Firstly, a set of core principles guide the development of the MTIA software stack. These include being PyTorch native, which we'll describe in more detail shortly, achieving both high performance as well as high developer efficiency, balancing the hardware heterogeneity requirements of our AI systems with the requirement of leveraging the unique advantages of MTIA hardware, building everything in a simple and composable way so that it can change and adapt quickly, as well as supporting scaling the system across many different axes, including number of devices, types of models, number of models, model sizes, etc. Now we can talk about PyTorch runtime integration. Engineers familiar with using GPUs in PyTorch feel right at home with MTIA devices because of the native PyTorch integration that MTIA software has. MTIA is a first-class PyTorch device, which means that you can use it just like you would use CPU or CUDA devices in PyTorch. There are MTIA device tensors, just like CUDA device tensors, for example. Additionally, libraries that are built on top of PyTorch can add support for MTIA with very little effort. It supports eager mode and graph mode execution, which are the 2 main execution modes in PyTorch. Eager mode means you can run one operator one right after another on the device without any changes to your model. Graph mode means that you can precompile, fuse, and optimize large chunks of the model together for maximum performance. It's also possible to mix and match these 2 different execution modes for maximum flexibility. On the right side here, we have a code snippet showing how easy it is to run your model using PyTorch and eager mode on MTIA devices. It will look familiar to anyone who's used to using PyTorch. Direct integration with PyTorch 2.0 allows model owners to achieve peak performance on MTIA hardware with very minimal effort. This includes graph capture using Torch Dynamo and Torch Export, and a backend optimizing compiler integration using Inductor. This also will provide out-of-the-box support for thousands of PyTorch operators in both eager mode and graph mode on MTIA devices. We're also able to leverage all of the latest technologies in the rapidly evolving PyTorch 2.0 compiler stack to achieve peak performance on new model types, as well as make models that are already running on MTIA hardware faster automatically. Another exciting thing that we've been working on is Triton language integration. Complex kernels can be written succinctly in the Triton language and run efficiently on MTIA devices. Triton allows users to efficiently write fused kernels for MTIA devices. Also, any existing Triton kernels that run on other device types can be easily ported to run on MTIA hardware. MTIA supports inductor-generated fused Triton kernels as well. These modes of integration can also be blended together as well, which means users can handwrite some kernels on Triton and also allow the compiler to auto-generate other kernels for maximum performance across the entire model. Now let's talk about the fact that MTIA supports key features that are required by the AI systems that it powers. Some examples of this include real-time model updates, which allow our AI systems to learn and adapt quickly to new information. It also includes dynamic shape support, which allows the input types to models to change over time, which makes deploying models even more flexible. Sequence models are at the heart of a lot of the latest model technology innovations, and we have a lot of support for these built in order to get maximum performance across a wide variety of sequence models out of the box. Investments in great tooling allow engineers to peer into the MTIA hardware to diagnose and fix issues very quickly. MTIA Insight is one such tool. It gives full, detailed information about the MTIA hardware to engineers who are using it. We also have model, operator, and instruction level tracing to get detailed information about what the hardware is doing at any moment in time. There's also kernel debug support, which allows engineers to look at what kernels are doing when they're running on the devices. Finally, we have numerical analysis tooling, which helps analyze when a model is giving incorrect results and root cause the issue. Now let's discuss model enablement. The MTIA software stack has been put to the test across a wide range of model types and applications. Some of these applications include advanced late-stage ranking techniques, very efficient early-stage ranking, several different Gen AI use cases, as well as content understanding models. Finally, looking towards the future, we're focusing on ensuring that new models can automatically achieve full performance on MTI hardware out of the box. This includes building generic model compiler optimizations that will work across many different model types, building out a self-service model optimization platform so that users can immediately get maximum performance on MTI hardware using their models, and also building auto-tuning functionality, which enables the system to configure itself to achieve roofline performance on the hardware without any manual effort. That wraps up what we've been working on MTIA software. Now I'll hand it back to Joel for some closing thoughts.
Thanks, Jack. Now I want to go into results and future directions for the MTIA program. Let's start by looking at some model co-design examples that really tie together the software ecosystem and the silicon design. So let's look at a few different areas here. We focused on kernel optimizations for one, where we really tried to optimize kernels to take advantage of our offload engines and our memory hierarchy. Specifically, we focused on large gems because they're an important part of scaling up ranking and recommendation models. So if you take a look at the picture in the upper right, this is a diagram of a gem implementation that tiles the weights from DRAM into SRAM so that we can feed the dot product engines directly out of SRAM with that high bandwidth. Another thing we did in the gem space was actually create in software an auto-tuning framework so we could automatically generate different gem kernel variants for specific shapes optimized for our architecture. We also spent a lot of effort on the compiler side. We worked on graph transformations to generate the most efficient patterns for our architecture. So we, of course, did things like operator fusions. You can see in the picture on the bottom right, we were able to fuse, in this example, a transpose with 3 FCs in parallel that consume its output. And because they share that input, we're able to run them together and only read the input once. We've also been able to eliminate a lot of unnecessary data movement operators, and we've been able to provide custom tensor placement and graph scheduling, which you know can make a really big difference in terms of SRAM locality. Finally, I'll talk just a bit about the host serving stack, because we did a lot of optimizations there to be able to efficiently shard models across multiple cards, utilizing peer-to-peer over PCIe, and to be able to stack multiple model instances across cards so we could have a fully loaded system in production to get the most utilization out of it. So now let's look at some end-to-end results on MTIA to see where we stand. So we evaluated MTIA against our baseline deployment in the data center. And we evaluated it against a set of late-stage ranking models, some low complexity as low as 7 million flops per example, and some high complexity as demanding as 680 million flops per example. You can see in the graph on the upper right, we plot our performance improvements over a 7-month period of time. This is absolute performance at a rack level compared to our baseline. And in terms of capability, they're about the same in terms of peak flops. So it's a pretty equal comparison. And you can see that performance improved over time, but particularly as we onboarded new models, the time to optimize a new model went down. So our developer efficiency was improved. Now let's look at the graph in the bottom right. So you can see that we get equal or greater performance at the rack level compared to our baseline. And if you look at lower complexity models, sort of out of the box, we have an advantage because we can utilize that on-chip SRAM that we built intentionally for that purpose. You can see on the high complexity model space, we need to do more optimizations to get good performance. So like I talked about, we need to block those gems in SRAM. We need to do more operator fusions to keep all that data on chip, and that'll get us higher flops. In terms of perf per watt, we're equal or better than our baseline, and all except for the most complex model, where there's some ongoing optimization work, and we believe that should be a parity. And then in terms of model flops utilization, the low complexity models exceed the baseline. The high complexity models are still behind, but there's a lot of perf headroom here, and so we'll spend a lot more effort optimizing this in the future. So now that we've seen some results, let's look at some of the opportunities for MTIA going forward. The graph on the right shows that there are different architectural requirements depending on the class of workload. And the class of workloads also changes over time. So when we first were designing MTIA, we focused on recommendation and ranking models, but now we're also focusing on Gen AI. And you can see that there are different compute, different memory, different network requirements across training versus inference, and across recommendation versus Gen AI models. So we must really balance kind of the specialization for these different domains across, sort of the maintainability and the effort of doing those designs, so it's something we can deploy and maintain in practice. The other thing to consider here is that we're seeing a great increase in scale of models, particularly in Gen AI domain. So we really have to focus on efficiency because power is going to ultimately determine what we can deploy. And then finally, like we've talked about, the developer experience is so important here. And so we really need to be able to move at the speed of model innovations. And so that'll mean keeping up with the pace of PyTorch changes and being able to keep up with the latest, most exciting models. So we're really looking forward to the future of MTIA, and we appreciate your time. Thank you very much.
Thank you, co-design and hardware team. Finally, we will close the event with a panel discussion. Our panelists are Michael Suo from Meta, Chip Huen from Voltron Data, and Chris Latner from Modular AI. Handing it off to Damien, who will moderate the conversation.
Welcome to all of you, and thank you so much for being here. By the way, for the audience, as I mentioned before, we asked for audience questions. That's why I'm holding an iPad. So we'll see what hard questions you have for our panelists. But let's kick off with just some intros. So joining us, we have Chris Latner, who is the CEO of Modular, and you almost certainly also know him as the co-founder of LLVM and Swift in previous lives. Chip Huen, who's like the best-selling author of designing machine learning systems and currently at Voltron, and Michael Suo, who is the technical lead for large-scale training at Meta within the PyTorch team. And rather than doing kind of bios and everything, I thought it would be fun to just ask all of you, and I guess we'll start with Chris. Can you share just a little bit about kind of your personal journey that got you into AI? Obviously, you started out in compilers, moved into AI. What was that about?
For me, it was really about, so I was leading the developer tools team at Apple with Xcode and Swift and Clang and all this stuff. And I just could not figure out how photos could understand what was a cat versus a dog. And this was 2016 kind of time frame. And when you're in charge of like helping people build and solve problems and build apps that can do things, it's like, how does this work? And so I fell down the rabbit hole of saying, well, I don't know how to write for loops to tell if something's a cat versus a dog. And so for me, that's where it all started. And from there, went straight through applied applications and self-driving cars, the infra side, scaling Google TPUs, a lot of embedded stuff, weird chips, a lot of the hardware-software boundary, which is where I naturally gravitate towards. But it was really that, cats versus dogs.
That's awesome. Chip, I guess I have the same question for you.
So I have like the good answer and the real answer. So the good answer is like, oh, AI can like get rid of the language barrier and then we can communicate and the world is wonderful. But the reality is that I just got into AI because I didn't want to deal with segfault. So I was taking some database classes and it was like really painful. And then there was these AI classes where you can just write like algorithm to play games like Pac-Man. It was like, yes, that's a lot more fun.
That's awesome. Michael?
Yeah, well, I started off my career in sort of distributed systems and data stores. So like many segfaults later, I was like wondering what to do with my life because I also did not really want to deal with that. And I think for me, I think AI was interesting because I saw like a lot of the problems that we have today have to do with how much information is out there and how can we make sense of this? And it's pretty clear now that like as people, we can no longer make sense of this information, but we need sort of tools to help us do this. And at the time that I joined, we didn't really have, the transformer. We didn't really have anything like that, but we had sort of the early sense of, there's cats and dogs in these videos, right? We had like LSTMs, this, the kind of like early inklings of what we have now. And it was really clear what the potential was. So I just kind of picked up, I joined the PyTorch team and haven't really looked back.
That's awesome. So we had a bunch of great questions from the audience, and let's start off with maybe one of the hardest questions in here. And I guess I'll mostly direct it to Chip, but I'm curious to hear thoughts from like all of our panelists here. So someone asked, what are your thoughts on models getting to AGI, and more specifically, what is the threshold? Like we all talk about AGI as being kind of a goal that we're pursuing. What does that mean? Like, what's the threshold for us getting to AGI?
So just before this, we had a rock, paper, scissors, and I lost, so I got the AGI questions. So it really depends on how we define AGI. So whether it's like average general intelligence or it's like absolutely godlike intelligence. So I think like it's just like generally average intelligence. I think we are there. I feel like for a lot of tasks, I much prefer like working with AI than with the average person, like working on this task. And for the godlike intelligence, I think that I'm not sure we wouldn't ever get there, because I'm not sure I have the experience, but like for whatever task I use AI for, it's usually really, really good. It's like 99% of the way there. But then just something really small, and you cannot get it to like do right. So I'm not sure we will ever get there, or we just have like this like pretty good AI that can do like get us like 90 or 99% of the way there, and then we have to build like other tools around it to make it work.
You don't think that a data center the size of a city will solve the godlike AI problem?
I mean, I really like that framing, right? I think when we talk about AGI, it's almost like a religious question, godlike, right? Because I think we don't really have a coherent understanding of how to measure intelligence. What do we consider to be intelligent? So I think like task-based approaches, right? Like, would I use an AI rather than a person for this class of tasks, given that the latency or whatever of the AI is likely to be much better? And I agree that like for a lot of things, we're kind of there. And the generality of it, I think, is really hard because it just eludes definition, kind of, right? Like you like work out on all these different tasks, and then somebody poses a new task. Is it really important that our AI be like fully general? I don't know. I don't think people are fully general either. So I think it's more important to talk about sort of like usefulness on specific tasks that we care a lot about.
I guess that actually dovetails into another audience question, which was around really like scaling laws. And right now we're seeing kind of this huge like exponential increase in kind of the amount of like data, power, everything that goes into training these models. What do you all see as the trends going there? And maybe I'll pick on, since I picked on Chip for the first one, I'll pick on Chris for this one.
Well, so I think scaling is massive. It's both in terms of the training side, which is what people would naturally think about when you're asking the question, but it's also in consumption. Right. I mean, as you look at what Gen AI has done, it's actually entered the public consciousness. It's actually starting to solve problems for people. And what that means is the inference side of things ends up maybe not being the only thing, but it's massively scaling. At the same time, what you have is you have a scaling, which people generally don't talk about, which is a talent scaling problem. How do you get more people to build AI and Gen AI and all the different things in the space into their products? And that becomes an accessibility question that I think there's a massive unlock potential for just making it more, so it's not just the biggest companies in the world that can do this, but it's so that average developers, whatever that means, can actually build these things in their applications. And I think that when you start looking at this, it's hardware scaling. Maybe not one vendor is the only one that builds all the chips. Maybe we should have multiple vendors, right? And how do we get communities of people that can scale across the different levels of abstraction needed to build these massively complicated stacks that are doing amazing things? So to me, I look at it scaling both in terms of flops, yes. I think that will also scale, but it's also about things like how do we build products, right? And I think that's the real unlock that we're all seeing and looking for.
And what do you think of the bottlenecks there? And I think one of the other questions by way from the audience that I was going to ask all of you was, how does someone who is not currently like specialized in AI get into the field? Because that feels like one of the big bottlenecks that we're facing.
Well, so I mean, I don't know how spicy of a take you want, Damien.
As spicy as possible.
Well, so PyTorch is brilliant because if you go back to 2017 when PyTorch was rising and TensorFlow was faltering and like this whole thing, back in the day, the old timers would say that we're on a quest to democratize AI. Right? I don't know if you've heard that for a number of years, right? We've kind of forgotten that. Well, PyTorch democratized AI. Success, right? And now roughly every computer science student graduating from college knows how to train a model thanks to PyTorch. On the other hand, PyTorch didn't democratize deployment. And so model deployment is one of these problems. It's just really, it's a dark art. Like I mean, speakers today were talking about how hard this really is, and this is very undemocratized. And so to me, I think that it's very much about software, it's about systems, it's about the fact that there's so much complexity at every level of the stack that, you know, it got created and hill climbed and changed, and none of these systems were built for Gen AI. We need a reset. And this is what we're working on at Modular, of course, but this is a really huge opportunity, but it's really hard, right? You need to actually be able to do the fundamental work, and you need to not be on a 6-month, I have to go deliver impact in a short window. You need to be able to do these really deep, fundamental, hard tech problems like solve compilers and programming languages and GPU coding and like all these things, which are all really, I think, mature concepts, but the reality of them is still a hot mess. And it's a gigantic disaster, depending on how you want to lean into that.
Yeah, I mean, I totally agree. I mean, on the question of how would someone, you know, with a background in computer science, who's a software engineer, but doesn't know that much about AI, I think that was kind of like me in 2016, 2017. I was like, I joined, I was like, man, I feel like I'm too late for this, right? Like, we've already figured out how to do sort of image classification. We've already kind of, the sort of framework side of things had been firming up. And it turned out, no, like there's so much runway left, and there's so much innovation, there's so much potential for improvement, because honestly, we're at the very beginning. Like the maturity level of these stacks for the kinds of things we're asking them to do is almost non-existent. We're like inventing things as we go along, and a lot of the problems are problems from other domains in computer science, right? There's compiler problems, there's just like, you know, production management problems, there's hardware problems. And so I think that, you know, if somebody was looking at, you know, how do I get into AI right now, I think it's just find the place that you're passionate about, find where you can add value to this stack. I mean, it's totally, like, it's completely, you know, from programming language all the way down to the hardware, completely open, because it's stuff that we're all just trying to figure out. And I think, you know, there's never been a better time in terms of like the materials available. You know, like Andre keeps putting up a new YouTube video every week, and like it's really like, you know, part of the openness of the ecosystem makes it really easy to learn and get familiar with, which is awesome.
Just to plus one you really quickly, hilarious. In 2017, I thought I was too late.
Yeah.
I thought all the best work had been done.
Chip, I know you've actually taught this at Stanford, so I'd love to hear your take on it.
So I do agree with both Chris and Michael that like productions is actually like the way to go right now. So I feel like I do think that's like if I were an educator, I think that's like an absolutely required assignment for everyone is to go out on the weekend and just try to make note of like how many of the people they interact with wouldn't be replaced by AI. So like, I will go to a fast food restaurant, so go to like a DMV, and I see like, okay, when is this person be replaced by AI? Okay. People told me that I should not bring this up in public because that's not a nice thing to say. But I do think it's like, I just like tried it, and I think it's like a lot of things just so painful. And you can just like totally see that like, why are people not using AI for this? Like, why are we still like making companies paying, like making customers suffering through all of this? Why it could be like, I don't know, like 5 minutes like through AI. So for example, like call center. Actually, I'm not sure if people saw this recent very popular Reddit thread. It's about like someone who worked at a call center, and like as soon as that person saw a demo, he was like, I'm looking for a job. Like, it's just like, you see like there's so many people working in call centers today, and it's just, I think it's a prime example of like things it's like we can still need a lot of GPUs for. But also like there are other stuff. So I was like doing this like text to speech, and even though it's like pretty good, and we have like many new voices coming out, but it's also that I feel like, why are we still not using those in daily life? So maybe there's a lot of like kinks, like quirks. For example, I was using text-to-speech from Google. I tested out like Google 11 Labs. I tried to use OpenAI, but somehow they got rid of all their voices. Like they don't have a text-to-speech API anymore. I don't understand why, because they have really, really strong voices. But like, they're very good. But then they do something dumb, like if you say like, hey, the character pauses. So like if you were a human doing narrative, right, you could pause and then continue. But the AI is like pause, continue. Or like it can't say the initial, like it's like IMO, it was like emo. Like it's a lot of small things like this was like very painful, and I feel like a lot were trying to build like really big models to make better text to speech, but I just want somebody to let me do like something like audio surgery. Like it's like, okay, here's the audio, I just want you to correct this one word. Like I just want to do it. I don't want a whole new model. I just want it to be better at one specific thing.
That's awesome. Thank you. I'm looking at the time. I think we have time for like maybe a couple of questions, and I'll kind of address those to all of our panelists. But let's start off with, someone was asking, we've all heard about acquiring, powering, and dealing with GPUs as kind of one of the bottlenecks that we all have right now in AI. What do you see as the next challenges and bottlenecks in infrastructure for either training or inference? You can
I think that it's really funny. Like one of the advantages of being in the industry for decades now is that you get to see trends and you get to see cycles, and you start to realize that if you zoom out, today everybody's talking about Hopper, stock out, availability, and how big of a cluster you can make and things like this. But zoom out and look out 5 years, right? So get out of exactly what letter comes before 100 or something. What I believe is that there will be a lot of hardware because everybody's making their own chips. What I believe is that there's going to be a lot of personalization, like a lot of wearables and other things, a lot of IoT, a lot of other places where AI will pervade our lives in all kinds of products. What I believe is there's going to be a lot of software developers that want to be able to deploy and build applications for these systems. And so I think that the grand challenge is like getting it so that we can close the gap between the software community and the hardware community. Because right now, people building chips, this software thing is a very amorphous, very difficult to access concept, and AI is moving so fast, which is one of the most beautiful things about it. On the other hand, you get to a lot of the application level people, and they really don't want to know about the silicon. They need it, but they want to think about the algorithms, right? And so I think this is a grand challenge. And so I think that as we scale into this, I think one of the great opportunities for us all is to innovate at every single level of the stack. Like I'm sure that there'll be, maybe SSMs will rise or something, and the transformer will have a new tweak that will totally change the trajectory of everything, and some new KV cache optimization of the day will amazingly transform how we think about things. But it's really, again, this tribe. Like, how do we get people talking to each other? How do we break down the boundaries? How do we enable this innovation to flow more freely? And I think that's really the macro challenge when you look across years of development, because nobody wants it to slow down. I mean, I shouldn't say that. Some people, I'm sure, do. I don't want it to slow down. I think that it can go even faster. And so I think that's what the way I look at the world.
Yeah, I think in terms of bottlenecks, unless do you want to do another question?
We got a couple of minutes. Go for it.
I think, in terms of training, I think in addition to GPUs, I think the other big thing is, right, like the availability of training data. I'm looking at our data infra folks. I think our hunger for new, different, varying data sets, like clean data sets that have been vetted in various ways, like legally or policy-wise, I think it is only increasing, and we're having, I think across the industry, a lot of trouble getting good, high-quality, clean data. There's the whole debate about synthetic data and what that might look like. And so I think, luckily the industry and, our field in general has a lot of experience with sort of very, very large-scale data management. But I think sourcing that data is going to be a big problem. And I think, starting from the beginning, right, like should we be putting more like sensors out into the world so that we can get good sequence data for some of these things is the sort of stuff we're going to start looking at, right? How can we get just really high quality data from not just what's already there on the internet, but like actually going out and collecting more is kind of an interesting thing that I expect to see in the next few years.
Yeah, so I think it's like, I would think that like data, I think it's like another electricity. I think we're consuming data centers like 2%, 1 or 2% of the world electricity, so we have like a 50 times more to go, which is like not even like 2 orders of magnitude. So another thing is regulations, make it easier for people to like use AI.
Actually, it kind of dovetails fairly well into the last question. We only have a couple of minutes, but I guess Chip, I'll point that one at you as well. So someone was asking, we've talked a lot about open innovation and openness today. And the question was, I guess it's almost something I should be answering, but I will put it back to the panel, which is like, why is Meta like investing so much in PyTorch and open source technology? But I guess like, Chip, from your perspective, like, how do you see the value of building this, in the open and open source as opposed to kind of more proprietary solutions?
I'm very cynical about this. So I think like open source has a lot of values, but the question like who do they have values for? So of course for users, it's for the third-party AI providers, right? Like they can take an open source model and commercialize it and make money. But I was like, let's say that like, say you have the best possible model in the world. Would you put it out for free? Or would you like make money off it? Right, so I feel like yes, maybe right now Meta is doing it because like Meta is trying to catch up to this whole race of like AI. But the question is like once they get there, will they continue making it open source?
I don't think Damian's allowed to answer that question.
I'm not going to directly respond to that, but I think I'll just say we're pretty committed to this. But time will tell, right? But it's a very fair question, right? But
and on the sort of subject of like setting aside the models themselves, but just like our investment in PyTorch, for example. I think a big part of it is, as we talked about, I think openness is really important because if Meta were to close off and sort of focus on our own infrastructure, our own software, you're essentially saying we're betting on us versus the entire world in terms of innovation. And for PyTorch, we have a position where we have a really strong ecosystem, like all these new techniques. Anything new is either originally the reference implementation is in PyTorch, or you wait a few hours, someone will put up a repo in PyTorch. And I think that's like a really powerful concept. Like we can all, if we make PyTorch better, it kind of accelerates things overall, and we can,
force multiplier.
Right? Sorry?
It's the force multiplier.
Yeah, the force multiplier. And then we can bring it back to and improve our products pretty rapidly because we're like, okay, we use PyTorch, it's pretty easy to incorporate and build on top of what the community has and contribute back. So I think, from that perspective, if you have something with such a large force multiplier, it's like, how could you not invest? And luckily, our leadership, Damian, and all the way up to the top, they like pretty internalize the value of that sort of thing. So I think that's why we continue to invest.
I would also zoom out. I mean, PyTorch is amazing, obviously. I think that that's clear. The work on the Llama models is profound, right? Because I think that one of the things that we as an industry struggle with, and I don't think that all the answers are there, but one of the answers we have are, will the models be proprietary and locked up? And one of the things I think is really challenging when you're talking about building these things into a business is the fact that if you're using some endpoint solution with either a proprietary or an open source model, it's really hard to build on top of that when you don't know if it's ever going to change. And so a lot of, I think, the Llama work and many other researchers across the internet and things like this and the open collaborative nature of AI, I think, is enabling a lot of people to build products with AI at their core. And I think that that openness, the transparency, the sharing of the models, which I don't think that Meta has to do, and I hope that it continues, and who knows, Chip, I understand the skepticism, but for as long as that happens, it's an amazing thing because it's really catalyzing tons of innovation in lots of different ways. And I think a lot of people that I talk to on the business side of things, when they're building into this Gen AI thing, the natural thing to do is to reach for some well-known company's endpoint, but then the problem is that their evals drop. Like on a Thursday, and I have no idea what's going on, right? And it's like, wow, that's really bad. Or I have to send all of my traffic across the open internet to this endpoint, right? I need to send this company my data so they can fine-tune their model on my data, right? And I think that this is things where what Llama and what open technologies allow to happen is we get to kind of fix some of those problems and we get the flywheel going. And does it go forever? I don't know. I mean, fair point, and I hope so. But I think that's really powerful. And so I think that a lot of the power and a lot of the progress in AI, even back in the days of TensorFlow or whatever, have really been made possible by the sharing. And I think it's amazing.
I just want to correct myself. I feel I shouldn't have said that at the Meta event. I think this Llama model is incredible. I think this I think PyTorch is incredible. So I'm really glad that Meta is one of the few companies just investing a lot of money. It's not cheap to build something like Llama 3. So you're actually investing money, and you actually really have really good people. And I was asking a lot of my PhD friends which labs you want to work with, and Meta AI lab is always the top 3. So I think But like, it's really incredible. So I just want to say that.
Yeah.
I can attest to building this stuff is very expensive.
On that note, I think we're slightly over time, so I'd like to thank our panelists for joining me today, and thank you very much.
Thanks for tuning in to our virtual edition of AI Infra at Scale. We hope you enjoyed the talks. Please visit the At Scale website and At Scale YouTube channel for future events.